JWST stared into a legendary cosmic battlefield and found two faint red pinpricks that looked like the first galaxies, light from just 200 million years after the Big Bang. Then, a year later, they moved sideways across the sky. If they weren't at the edge of the universe, what were they really? And what does their disguise reveal about how we hunt the dawn of time? In deep space, the most dangerous illusion is the one that looks exactly like first light. Tonight, the James Webb Space Telescope forces a reckoning about distance, certainty, and the stories we build from faint heat. What happens when the universe offers a perfect signature and our best methods agree too quickly? In the bullet cluster, gravity turns space into a lens, magnifying the background, warping the evidence, and daring us to overinterpret. We will follow the chain of reasoning that transforms a few photons into a cosmic age, and we will watch that chain strain under its own precision. Because the frontier is not only far away, it is also crowded. The infrared sky is packed with objects that hide their true nature behind the same colours, the same dropouts, the same convenient breaks between filters. When a source is barely there, every assumption becomes louder. About dust, about hydrogen, about how galaxies should look when the universe is young. This film is an expedition into how astronomy decides what is real and what is merely plausible. We will step inside the toolkit that has guided the search for primordial galaxies for decades, and we will see why it usually works even at the edge of detectability. Then we will add a different kind of evidence, one that does not care about templates or expectations, time itself. A year can be an instrument as sharp as any spectrograph. With patience, the sky becomes a measuring grid, and stillness becomes a claim that must be earned. In that waiting, subtle shifts and stubborn non-shifts start to separate the distant from the nearby, turning a romantic narrative into a testable one. And beneath the statistics lies a deeper question about discovery. If the earliest galaxies and the coldest wanderers can wear the same infrared disguise, what does that imply about every headline built on a handful of extreme dots? Not a scandal, but a discipline, an invitation to improve our filters, our priors, and our courage to be corrected. Along the way, we will enter a strange overlap where cosmic dawn and the outskirts of our own galaxy share the same faint glow. We will learn why hydrogen at the beginning of time can resemble methane next door, and why a point of light can be either a newborn city of stars or a solitary failed sun. The edge we are chasing is real, but it is softer than we imagined, and it demands proof that travels on more than brightness. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. From the bullet cluster's warped deep field to the physics of dropouts, motion tests, and spectra, we will trace how certainty is built. And when the method is challenged, we will see what the challenge teaches us about the true boundary between our galaxy and the early universe. The first sign is almost nothing, the kind of almost nothing that hides in plain sight. Two faint red dots sit in a JWST infrared frame, buried deep in the bullet cluster field. They are not bright, and they are not dramatic, and they do not announce themselves with a clean arc or a glowing halo. They are simply there, two small points where the background should be thin, smooth, and statistically boring. On the screen, the image looks like a quiet snowfall of distant light, each speck a galaxy or a star or a noise fluctuation. The two dots are different, though, because they hold their colour across the right filters. A pipeline flags them as extreme candidates, not because they look pretty, but because they behave like outliers. Their colours match what astronomers expect from the earliest galaxies, when ultraviolet starlight has been shifted into the infrared. In the moment of discovery, the room goes quiet, and the quiet has a particular weight. The numbers on the screen do not fit the usual timeline, and the usual timeline is what keeps the universe coherent. These dots are red in the specific way that matters, which is a technical kind of red. They vanish in shorter wavelengths and persist in longer infrared bands, as if a curtain has been drawn across the blue end of their spectrum. That pattern is a classic dropout signature, and it is one of the oldest tricks in observational cosmology. It can mean light has been stretched by expansion across most of cosmic history, until the original wavelengths no longer land where our detectors first look. In practical terms, a dropout is a missing detection that becomes a clue because the absence is structured. A sharp spectral break can erase the galaxy from one filter and let it reappear in the next, like a lighthouse beam sweeping across a shoreline. The team runs the first checks quickly, because the first checks are where false miracles die. They test calibration, noise spikes, and detector artifacts that can mimic faint sources when the data are pushed to their limits. They check that the dots repeat across exposures, because real astrophysical objects should survive time and dithers. They confirm the signal holds through different reductions and independent pipelines, each with its own assumptions about backgrounds and cosmic rays. They measure shapes and sizes, even though the sources are barely more than a few pixels across. The sources look compact, consistent with distant objects that are small in angular size and possibly magnified by lensing. They also look for the subtle fingerprints of a bad pixel or a transient hit, because those can masquerade as point sources. In deep imaging, the line between discovery and artifact is often a single stubborn defect. They do what every cautious group does next, which is to ask whether the field itself could be tricking them. In a lensing field, the sky is not a neutral backdrop, and the foreground mass can sculpt the background into misleading shapes. Because this is not any random patch of sky. This is the Bullet Cluster, a famous cosmic collision with a long history. Even in still images, the Bullet Cluster feels like a scene after impact, with structures that look displaced and unsettled. Astronomers know it by its catalogue name, but they remember it as a narrative. Two clusters that did not merge gently. Two galaxy clusters passed through each other at high speed, likely several thousand kilometers per second. Hot gas slammed together and slowed, while the galaxies themselves kept moving, because the space between stars is so vast that direct collisions are rare. The separation left a mappable signature that reads like a forensic diagram. X-ray gas sits in one place, glowing from shock heating, while most of the mass appears offset from it, inferred from how it bends light. That offset became iconic evidence for dark matter, because the dominant gravitational mass did not follow the dominant ordinary matter. Gravitational lensing showed mass where little baryonic matter glowed, and the mismatch was hard to explain away. The Bullet Cluster is studied because it is a laboratory, and laboratories are where theories meet stubborn reality. It tests how matter behaves when gravity and collisions disagree, and it limits how strongly dark matter can interact with itself. It is also studied because it is useful in a very practical sense. Its mass bends light and magnifies whatever lies far behind it, turning the cluster into a natural telescope with no moving parts. In astronomy, gravity can act like a telescope, but it is a telescope with personality. A massive foreground lens stretches and brightens background galaxies, and it can also shear them into arcs that look like brushstrokes across the sky. The Bullet Cluster lens is strong and complicated because the mass is not a single smooth ball. It creates arcs, distortions, and sometimes multiple images of the same source, depending on where the background galaxy sits relative to the lens's critical curves. That complexity is a risk and an opportunity, and the two are inseparable. It can boost faint objects into view, and it can confuse their identities, because a single galaxy can appear twice, or appear brighter than it truly is. JWST was built for this kind of hunt, and the hunt is fundamentally about wavelength. Its infrared sensitivity reaches the bands where early galaxies should appear, after the universe has stretched their light beyond the reach of optical telescopes. The telescope does not see the universe as it is now, even when the image feels immediate. It sees light that left long ago and only arrives today, carrying the conditions of its origin like a timestamp embedded in colour. So what does the edge of the universe mean here, in a frame full of faint points? It is not a wall, and it is not a place you could reach, even if you could travel forever. It is an observational limit, and the limit has several causes that stack together. It is the point where sources become too faint, too redshifted, or too rare to detect, given the sensitivity and the noise of our instruments. Cosmic expansion stretches light as it travels, and the stretching is continuous, not a single event. Ultraviolet and visible photons from early stars slide into infrared bands, and the galaxies that made them fade as their light is diluted across an expanding space. Redshift is the bookkeeping for that stretch, and it is also a clock. Higher redshift means earlier emission, and a younger universe at the source, although the exact conversion depends on the cosmological parameters that describe expansion. The team fits photometric redshifts first, because photometry is what the image gives them immediately. They compare the dot's brightness across filters to libraries of galaxy spectra, looking for the best match to a redshifted template. This is a statistical method, not a single decisive measurement, and it carries its own vulnerabilities. A few data points across broad filters can hide multiple solutions, especially when the object is faint and every flux measurement has uncertainty. Still, the best fits land in a shocking range, and the shock is not theatrical. The implied redshifts suggest light emitted within 200 million years after the Big Bang, when the first generations of stars were only beginning to transform pristine gas. That number carries weight because it sits near the beginning of galaxy assembly as we normally picture it. It pushes into an era when galaxies should be small, sparse, and hard to make luminous, especially if they have not yet built up heavy elements that help gas cool. In the standard picture, early star formation begins in dense pockets of dark matter halos where gas can collapse. Yet making something bright enough for JWST to see through a lens that is not infinite is a higher bar than merely forming stars. Models allow early star formation, but not necessarily in abundance, and not necessarily in such clean detectable packages. Bright galaxies that early strain typical assumptions about how quickly gas can accumulate, fragment and convert into stars without being blown apart by feedback. If these dots are real, high redshift galaxies, the timeline shifts in subtle but consequential ways. Structure would have assembled faster than many forecasts, and the earliest luminous systems would have had to be more efficient at turning gas into starlight. It would change how we think about the first stars, even if those stars are not directly seen. It would change how quickly gas cooled, collapsed, and enriched, because early supernovae seed the next generation with elements that alter cooling and opacity. It would change how ionization begins, which is one of the great phase changes in cosmic history. The earliest galaxies are candidates for turning the neutral universe transparent by emitting enough energetic photons to ionize hydrogen across intergalactic space. Yet the claim is also fragile, because photometric redshifts can be fooled in ways that are well known and still dangerous. Nearer objects with dust, strong emission lines, or unusual spectra can masquerade as ancient galaxies when the data are sparse. A dusty galaxy at moderate distance can look red, because dust absorbs bluer light and lets redder light pass through. A cool star in our own galaxy can mimic a dropout in some filters, especially if its atmosphere imprints molecular absorption bands. Even lensing can mislead, because magnification changes apparent brightness and can bias selection. Lens models can shift inferred distances and sizes, and they can make an ordinary object seem extraordinary if the magnification is overestimated. So the team tightens the tests, moving from excitement to discipline. They check whether the colours could be produced by known low redshift templates, including dusty star-forming galaxies and extreme emission line galaxies that can spike a single filter. They look for telltale flux in bands where a nearby object should appear even faintly. They find almost nothing, which strengthens the case, because a lower redshift interloper usually leaks some light into the wrong places. They compare the sources to other high redshift candidates, because context matters in colour space. The dots sit in the right region of the diagnostic plots, almost too cleanly, as if they were drawn there by a textbook rather than by nature. That cleanliness is part of the unease, and the unease is rational. Real data is messy, and real galaxies often show hints of complexity, such as partial detections, asymmetric shapes, or colours that suggest multiple stellar populations. The dots seem too perfect for the story everyone wants, and that is a warning sign. Two extreme candidates in a famous lensing field feels like a trap, because the field is already famous for producing dramatic illusions. The bullet cluster has been observed for decades, in optical light, in X-rays, and through lensing reconstructions. Many teams have searched its background for distant galaxies, and the field has a long memory in the literature. Now JWST arrives with new power, and the change is not incremental. It can see fainter, redder sources than Hubble could, especially through strong lenses, because its mirror and detectors are optimized for the infrared where early galaxies hide. The field becomes a proving ground, and proving grounds have a harsh logic. If JWST can find the earliest galaxies anywhere, it should find them here, where magnification can lift the faintest signals above the noise floor. That expectation adds pressure, even if no one says it out loud. A discovery in this field will be scrutinized, replicated, and challenged immediately, because the bullet cluster is a public stage in modern cosmology. The team debates what to do next, and the debate is not about ego so much as responsibility. They could publish quickly and claim a record, or they could wait and verify, accepting that someone else might notice the same dots. They choose to wait, and waiting is its own kind of courage in competitive science. The stakes are too high, and the consequences of a mistake would ripple through the literature, shaping models and telescope proposals before the correction arrives. They ask a simple question that is hard to answer, because the universe is good at ambiguity. Are these dots truly at the dawn of galaxies, or are they imposters, dressed in the right colours by dust or noise or lensing geometry? To answer, they need more than colours, because colours can be suggestive without being definitive. They need spectra, or at least deeper imaging that can break degeneracies, separating a true Lyman break from a dusty continuum or a line-dominated interloper. Spectroscopy is the gold standard, and the phrase is earned. It can reveal a sharp break, it can reveal emission lines, and it can lock a redshift to a specific wavelength shift rather than a best-fit probability distribution. In a high redshift galaxy, the key feature is often the Lyman alpha break, caused by hydrogen absorption shortward of 121.6 nanometers in the rest frame. When redshifted, that break marches into the near-infrared, and its position becomes a cosmic ruler. But spectroscopy is expensive, and expensive means scarce. It requires time, careful planning, and a target that may be too faint even for JWST, especially if the lensing magnification is less generous than hoped. They also need the lens model, because in a field like the bullet cluster, distance estimates depend on how mass is distributed. The lens is not measured directly, so it must be inferred from how it warps the images of many background sources. Lensing models are built from many constraints, and each constraint has uncertainty. They use arcs, multiple images, and the positions and velocities of cluster galaxies, and they often incorporate X-ray maps of the hot gas as an additional guide. Different models can disagree, sometimes subtly and sometimes meaningfully. A small change in the mass map can change magnification and inferred intrinsic brightness, and it can shift where critical curves lie by enough to alter the interpretation of a faint source. The team consults lensing experts because expertise here is a form of caution. They ask whether the dots could be multiple images of one background object, mirrored by the lens into two positions that look like separate galaxies. They check whether the positions align with critical curves, where magnification spikes and image multiplicity becomes likely. They test whether the lens could create a duplicate image nearby, faint enough to miss in one reduction and appear in another. The answer is not clean, and the lack of cleanliness is itself information. The lens is complex and the sources are faint, and the field is crowded with cluster members whose light must be modelled and subtracted with care. In the images, bright elliptical galaxies sit like boulders in the foreground, their halos bleeding into the background. Subtraction leaves residuals, and residuals can imitate faint objects if the modelling is slightly wrong. Still, the candidates remain, stubbornly present across the checks that usually erase mirages. They are not easily dismissed as artifacts, and they do not match common low redshift interlopers, at least not without twisting the templates into unlikely shapes. That is the tension at the heart of the chapter, and it is the tension that makes the dots feel alive. The evidence is strong enough to excite and weak enough to haunt, because astronomy often advances in that narrow corridor. Because if they are real, they are a message from the first 200 million years, when the cosmic web was still tightening. If they are fake, the disguise teaches a lesson about selection effects, lensing biases, and the seductive clarity of a clean dropout. The central question forms quietly, and it stays in the room long after the screens go dark. If those two red dots are not primordial galaxies, what are they, and why do they look ancient, as if the universe is testing our definitions? The team keeps the result close, not out of secrecy for its own sake, but out of respect for uncertainty. They share internally, they run more checks, and they resist the urge to announce, because announcements harden speculation into headlines. They know how the story would sound because they have heard versions of it before. JWST finds the earliest galaxies behind the bullet cluster, and the universe grows younger, and the first chapter of structure formation gets rewritten in real time. They also know how the story could collapse, and collapses have their own momentum. A nearby object with the right colours could erase the claim overnight, and the retraction would be remembered longer than the caution that preceded it. So they watch and wait, and waiting becomes an active process. They plan follow-up, they compare catalogues, and they look for any sign of motion or variability, because a star in the Milky Way might shift slightly, while a distant galaxy should not. They also examine the local background, checking whether faint gradients or residual light could bias the photometry. In deep fields, the difference between a detection and a non-detection can hinge on how the background is estimated. The dots do not change in the first pass, and that steadiness is reassuring without being conclusive. They sit where distant galaxies should sit, fixed against the deep background, and they refuse to resolve into something obviously nearby. In this opening, the mystery is set, and it is set in a place already famous for separating mass from light. A cosmic battlefield has produced two signals that may rewrite the early timeline, or may reveal how easily we can be fooled by the universe's own optics. Now the investigation begins, and the investigation will be as much about method as about result. To understand the edge of the universe, we have to understand the tricks that move it, and the assumptions that make it seem closer than it is. Next, we follow the data forward. The same field will be observed again, and the dots will be forced to reveal themselves. The two red dots in the bullet cluster field look like a familiar kind of miracle, the sort that makes astronomers sit up straighter and stop scrolling. They look familiar because observers have trained for this pattern for decades, through Hubble deep fields, through false alarms, and through the slow discipline of learning what the universe usually does. On the screen, the field is crowded with ordinary galaxies, smeared into soft ovals and faint arcs, each one a small island of starlight. The cluster itself sits like a bruise of gravity, its mass bending background light into subtle distortions that only become obvious when you know where to look. And then, almost casually, 2 points glow in the redder images, while the bluer frames show nothing at all. In the control room quiet, that absence is as loud as a detection. A blank patch in one filter, paired with a clean point in the next, is the kind of pattern that has launched papers, and occasionally retractions. The dots do not look dramatic in shape, yet their behaviour across wavelength looks scripted, like a textbook example hidden inside messy reality. When we say edge of the universe, we do not mean a wall or a border you could ever reach. We mean the edge of detection and interpretation, the farthest light we can reliably tag with a distance and a time. We mean the limit where photons are so few and the assumptions so heavy that every claim must be carried carefully. Cosmology turns distance into a measurement of change, because looking far away means looking back. The universe expands while light is in flight, and that expansion stretches every photon like a note sliding downward in pitch. What arrives at our telescope is not the same wavelength that left its source, and that difference is the clue. In the standard picture, the stretching is described by a scale factor, AT, that grows as the universe ages. Redshift, Z, is the shorthand for that growth, defined so that 1 plus Z equals how much the universe expanded since the light was emitted. In plain terms, a redshift of 10 mean space grew by a factor of 11 while the photon travelled. Distance in cosmology is written in wavelength, because wavelength is what the detectors actually count. A spectrum is not just colour, it is a record of physical processes, stamped into light by atoms, dust and hot plasma. When that record is stretched, the stamps move, and we can measure how far they have travelled. A young galaxy can shine hard in ultraviolet because its stars are hot and short-lived, burning fuel at a furious rate. Massive stars live fast and die young, and their surfaces pour out energetic photons that would be hazardous up close. In the early universe, those stars were often forming in compact turbulent regions, where gas was dense and the pace of change was quick. Those regions are not calm nurseries, but pressure cookers of gravity and feedback. Ultraviolet radiation heats surrounding gas, stellar winds drive shocks, and supernova explosions enrich the next generation with heavier elements. Even so, the earlier systems may have been metal poor, which can make stellar populations run hotter and bluer than many galaxies today. If that galaxy is extremely distant, that ultraviolet arrives as infrared, not because the galaxy changed its mind, but because space itself expanded. The photon's wavelength grows with the scale of the universe, so the same light is relabeled by our instruments. In plain terms, the universe makes blue light look redder the longer it travels. Redshift is the accounting system for that stretch, and it is also a time machine with units. A higher redshift means the light started bluer, travelled longer, and arrives shifted into longer bands. It also means we are looking further back in time, because the light left when the universe was younger and smaller. This is why deep infrared images can act like time machines. and why astronomers talk about them with a kind of reverence. They are not showing older light as red for aesthetic reasons, but for physical ones, because the early universe's ultraviolet has been dragged into the infrared by expansion. When you watch the filters step redward, you are watching cosmic history slide past the instrument. The idea is simple, yet the practice is demanding, because nature loves lookalikes. You cannot just look for red things and declare victory, because many objects are red for local reasons. Dust, cool temperatures, and molecular absorption can all tilt colours, and the sky is full of sources that would love to be mistaken for the first galaxies. For 30 years, the core hunt has relied on a sharp spectral cliff, a sudden missing slice of light that behaves predictably. That cliff is carved by hydrogen, the most common element in the cosmos, and the one that filled the space between early galaxies. Hydrogen is not merely abundant, it is also simple, and simplicity makes reliable signatures. Hydrogen does not absorb all light equally, because atoms have quantized energy levels. Photons with the wrong energy pass by, but photons with the right energy are swallowed, kicking electrons into higher states or freeing them entirely. Those thresholds leave missing chunks in spectra, like bite marks that can be recognized even when the rest is noisy. The simplest version begins with the Lyman alpha line at 121.6 nanometers in the rest frame, in the far ultraviolet. Photons shorter than that are strongly suppressed by neutral hydrogen, because they are resonantly scattered and absorbed. Even if the galaxy emits them, the space between galaxies can erase them before they ever reach us. Resonant scattering matters because it is not a one-time event. A Lyman alpha photon can bounce from atom to atom, zigzagging through the intergalactic medium until it is absorbed by dust or shifted out of resonance. That random walk turns what could have been a bright signal into a fragile one, especially when the universe is still rich in neutral hydrogen. Even more severe is the Lyman limit at 91.2 nanometers, the energy needed to ionize hydrogen. Below that limit, hydrogen can strip electrons completely, and absorption becomes brutally efficient. In spectra, this is not a gentle dimming, it is a near shutoff. In the early universe, the space between galaxies contained much more neutral hydrogen than it does today, because reionization was still underway. The intergalactic medium was not yet fully transparent to ultraviolet light, and that matters for every distant source. That intergalactic hydrogen adds absorption on top of the galaxy's own gas, deepening the cliff. Reionization is often described as a phase change in cosmic visibility. The first luminous sources gradually ionized their surroundings, carving bubbles of transparency that grew and overlapped. When we search for the earliest galaxies, we are also sampling how patchy that transition was, and how quickly darkness gave way to clarity. So a distant galaxy's spectrum is not a smooth rainbow. It is a continuum that suddenly drops, because the blue and ultraviolet side is erased by intervening hydrogen. The drop can be sharp enough that, in broadband images, the object practically disappears. That drop is the Lyman break, and it is the backbone of the dropout technique. It turns absence into a measurable feature, and it gives astronomers a way to find candidates without needing a full spectrum. In a universe where spectra are costly, that is a powerful trade. A telescope does not record a full spectrum in a deep image, not unless it is using a spectrograph. It records brightness through filters, each one a wide window in wavelength, and each window collects photons across a range. The result is a set of points, not a continuous curve, but the cliff can still show itself. If the Lyman break falls inside one window, the galaxy can vanish there because most of that filter's photons are on the absorbed side. If the break falls redward of that window, the galaxy reappears in the next where the photons are safer. The universe, in effect, slides the cliff through our filter set as redshift increases. This is the dropout in practice. The source drops out of bluer filters and survives in redder ones, as if the universe pulled a curtain across the shorter wavelengths. In a sequence of images, the object seems to blink into existence only when the filter is red enough. In Hubble's era, the curtain moved through optical filters as redshift increased, and the naming became a kind of shorthand. Candidates were labelled by the filter they disappeared from, like U dropouts and B dropouts, and later I dropouts and Z dropouts. Each name implied a rough redshift range, and each range mapped to a different chapter of cosmic history. There is history inside that shorthand because it reflects how instruments evolved. As detectors improved and filters multiplied, the community learned to push the break farther, one band at a time. Each new dropout class was not just a label, but a claim that the data had become deep and clean enough to trust absence. The method is simple to explain and hard to execute, because it lives on the edge of what the data can support. It depends on deep exposures, careful calibration, and honest accounting of non-detections. It also depends on understanding the instrument, because a false dropout can be created by noise, artifacts, or subtle background errors. A non-detection is not nothing in this game, and it must be measured with the same care as a detection. A non-detection becomes a limit, and limits shape which redshifts remain plausible. If the object is truly absent in a blue filter, that absence constrains how much light could be there, and that constraint can be as informative as a detection. Teams build color cuts to isolate candidates, using the logic of the cliff. They compare how bright an object is in one filter versus another, then look for extreme jumps that match the expected break. The cuts are not arbitrary. They are tuned with simulations, with known galaxies, and with the measured noise properties of the images. A true Lyman break galaxy shows a steep color between the last filter below the break and the first filter above it, because the flux changes abruptly. It also shows relatively flatter colors redwood of the break, because the continuum there is smoother. That second requirement matters because it filters out many things that are simply red everywhere. Dust can redden everything gradually, like a dimmer turned down more strongly at shorter wavelengths. A Lyman break is abrupt, while dust is usually a smoother slope across bands. When you plot colors, that difference becomes geometry. One path cuts sharply, the other drifts. Color plots make this logic visible. Candidates cluster in a region where the break is strong and the red side colors are consistent, and that region can be drawn as a selection box. On screen, it looks like a map with a fenced-off neighborhood, and the best candidates are the points that land inside. But color selection is only the first sieve, because the universe is inventive and the data are imperfect. The next step is photometric redshift fitting, which tries to use all filters at once instead of relying on a single color jump. It is a way to ask the whole dataset to agree on one story. Photometric redshifts treat each filter measurement as a data point on a coarse spectrum, with uncertainties that matter as much as the values. The algorithm compares those points to template spectra, shifted across redshift, dimmed by distance, and sometimes modified by dust. It is pattern matching, but with physics constraints built in. Templates represent different galaxy types and ages, because galaxies do not all shine the same way. They include star-forming continua, older stellar populations, and sometimes strong emission lines that can dominate a band. Some libraries also include nebula emission from ionized gas, which can change colors dramatically at high redshift. That nebula component is not a footnote, because gas can outshine stars in specific bands. Lines like H-alpha or O3 can pour into a broad filter and inflate its brightness, shifting colors in ways that feel counterintuitive. In the early universe, where star formation can be intense, those lines can be extreme and therefore dangerous. The code asks a practical question. At what redshift does a template best match the observed brightness pattern, given the uncertainties? It computes a likelihood for each redshift and then folds in assumptions about what is plausible. The output is not a verdict, it is a quantified preference. The result is not a single truth. It is a best fit redshift with a probability distribution that can have multiple peaks, especially when data are sparse. In the plot, you can see competing hills, each one a different universe the object might belong to. Those multiple peaks are the danger. A faint object with few significant detections can be consistent with very different physical scenarios, and the math will not always choose the right one. When the signal to noise is low, the templates can fit by coincidence, and coincidence can look persuasive. One common degeneracy is high redshift versus dust, because both can remove blue light from the observed bands. A dusty galaxy at moderate redshift can look red and faint in blue filters, mimicking the effect of intergalactic hydrogen. The difference is in the shape, but the shape can be blurred by noise. Another degeneracy is high redshift versus emission lines, because lines can spike a single filter upward. A galaxy with extreme lines can brighten one band and fake a break between bands, especially if the neighbouring filter is quieter. In broad filters, a narrow line can masquerade as a continuum step. A third degeneracy is high redshift versus cool stars, because some stellar atmospheres have deep molecular absorption bands that carve their own cliffs. These are not cosmic cliffs, They are chemical ones, shaped by temperature and pressure in an atmosphere. But in filter space, they can land in the same places. Photometric redshift fitting tries to manage these ambiguities by using more filters and better templates, and by treating uncertainties honestly. It also relies on priors, even when they are not advertised, because priors stabilize solutions when the data are weak. Without priors, the algorithm can chase improbable answers simply because they fit slightly better. A prior is an assumption about what is likely, based on what we already know about the universe. It can encode that very bright galaxies are rare at very high redshift, or that certain types dominate certain epochs. It can also encode the expected distribution of galaxy sizes or colours, which subtly shapes the final probability. These assumptions are not arbitrary, because they are built from decades of surveys, luminosity functions, and confirmed samples. The field has measured how galaxy populations evolve, how number counts change with magnitude, and how dust behaves on average. Priors are the accumulated memory of that work translated into math. This is why the method usually works. It is not one trick, but a layered toolkit that cross-checks itself when the data are rich, and it is anchored in physics that does not change from field to field. Hydrogen absorption is universal, and cosmic expansion is not negotiable. The Hubble Deep Field and its successors proved the approach at scale, because they provided data deep enough to build large samples. Large samples of dropouts produce consistent population trends across independent teams, even when the teams use different pipelines. When independent methods converge, confidence grows. There is also a cultural memory here, built in the 1990s and early 2000s, when deep fields trained astronomers to trust faint patterns. Teams learned how to subtract backgrounds, how to model the point spread function, and how to keep selection biases from masquerading as evolution. That slow craftsmanship is part of why a simple dropout still carries authority. Spectroscopic follow-up confirmed many candidates, and those confirmations were the gold standard. When spectra were possible, the Lyman break and emission lines landed where photometry predicted, and the redshifts locked into place. Each confirmation was a calibration point that improved future selections. The confirmations were not perfect, but they were statistically strong, and statistics are the language of surveys. When you have hundreds of candidates, a modest contamination rate can be modelled and corrected, and the population-level conclusions remain robust. The goal is not to be flawless for every object, it is to be reliable in aggregate. The method also thrives because the universe cooperates in a specific way. Hydrogen absorption is a universal physics feature, not a fragile astrophysical detail that depends on local conditions. Even when galaxies differ, the intergalactic medium still imposes its signature, and that signature is the same kind of cliff. Yet the method always carried a quiet warning. It is optimized for finding things that look like young galaxies, and it can be fooled by things that share the same colors. The warning becomes louder as we push to extremes, where the candidates are faint and the filter coverage is stretched. The risk rises when observations push into new wavelength territory. Every new band is a new arena where different imposters can appear and where old intuitions can fail. A selection box that worked beautifully in optical space can overlap with an entirely different population in the infrared. JWST changes the arena dramatically. Its mirror, detectors, and cold operating environment make it exquisitely sensitive in the near-infrared, where the earliest galaxies are expected to show up. The telescope's design reduces thermal noise, so faint infrared photons are not drowned by the instrument itself. That cold matters because infrared astronomy is always fighting heat. Warm hardware glows, and that glow can swamp the signal you want, so JWST hides behind a sunshield and radiates its warmth away. In the images, that engineering becomes a kind of silence, a dark background that lets tiny sources stand out. NearCam provides many filters across a wide infrared range, and that filter set is a gift to dropout selection. It samples the break with finer steps, letting astronomers watch the cliff move from band to band. In practice, that means tighter constraints and fewer ambiguous fits, at least in principle. At the highest redshifts, the Lyman break moves beyond the optical entirely. It slides through one infrared filter after another as redshift climbs, and each step corresponds to a different cosmic age. The hunt becomes a search for objects that appear only after a particular infrared threshold, so JWST extends the classic hunt into earlier times. It can search for galaxies whose ultraviolet has been stretched so far it lands beyond Hubble's reach, into wavelengths where Hubble was nearly blind. The promise is not just more galaxies, but galaxies closer to the beginning of starlight. In a lensing field like the Bullet cluster, that reach extends again, because gravity itself becomes part of the instrument. Magnification can lift sources that would otherwise be below the noise floor, and it can spread them into arcs that reveal structure. The cluster's mass, including its dark matter, acts like a natural telescope. Lensing also adds a subtle layer of interpretation, because magnification is not free. The same gravity that brightens a background source can distort its apparent size and shift its apparent position. To use the lens well, you need a mass model of the cluster, and that model carries its own uncertainties. This combination is why the two red dots felt plausible. Their colours match what a very high redshift dropout should do in JWST's infrared filters, and the pattern is not subtle. They vanish where the break should erase them, and they appear where the red side continuum should survive. Visually, the effect is almost theatrical. In the bluer ENIACAM panels, the positions are empty, as if someone erased the objects with a careful brush. In the redder panels, the dots return, small and steady, sitting among distant galaxies that look more ordinary. Clean patterns are comforting, but they can also be traps. JWST's infrared sensitivity opens a door to a specific kind of local object, one that older searches did not encounter as often. When you can see deeper in infrared, you do not only see farther away, you also see colder things nearby. In the Milky Way, there are bodies too cool to shine like normal stars. Brown dwarfs and planetary mass objects glow mostly in the infrared because their temperatures are low and their peak emission shifts to longer wavelengths. They are not powered by sustained hydrogen fusion, so they fade and cool over time. Their atmospheres are not featureless. Molecules like methane and water absorb strongly in bands that overlap JWST's filters, carving deep troughs in the infrared spectrum. The chemistry depends on temperature, pressure and cloud layers, and small changes can produce sharp colour differences. Methane absorption can create steep colour changes between adjacent infrared bands. Those changes can resemble a dropout, even though no cosmic redshift is involved and no intergalactic hydrogen is required. The cliff is atmospheric, not cosmological, but the filters do not know the difference. A cool methane-bearing object can be faint in one filter and brighter in the next. In colour space, it can sit near the high redshift selection box, close enough to raise alarms in a survey pipeline. If it is faint and isolated, it can look exactly like a distant galaxy candidate. This is the imposter JWST increases the risk of finding. The telescope is so good at faint infrared points that it can detect nearby cold wanderers in deep extragalactic fields, even when the field was chosen to study faraway galaxies. The irony is structural, built into the instrument's strengths. The same sensitivity that reaches the first galaxies also reaches the outskirts of our own neighbourhood, where dim objects drift through the halo of the Milky Way. These bodies are close enough to move, but faint enough to hide in older surveys. JWST can bring them into view by accident. Photometric redshift codes can be misled by these objects if stellar templates are incomplete or poorly sampled in the relevant bands. A brown dwarf can be forced into a galaxy template, and the fit can land at an absurd redshift because the algorithm is trying to explain a molecular trough with hydrogen absorption. The math will comply, even when the story is wrong. Even when stellar templates are included, the uncertainties can keep both solutions alive. A faint point source can be consistent with a distant galaxy and a nearby substellar object, because both can produce a sharp colour change. The probability distribution can split, and the split can be hard to resolve. This is where the method's assumptions become visible, because assumptions are easiest to ignore when they work. Dropout selection assumes the break is hydrogen, and the source is extragalactic, because that is usually the right interpretation in deep fields. Photometric redshifts assume the template library spans the true possibilities, which is a strong claim when nature is diverse. They assume the object is not a rare atmospheric spectrum masquerading as a cosmic cliff. They assume the source is not a moving foreground body that happens to sit in the same pixels as a distant galaxy field. And they assume that the noise behaves, because noise can also sculpt false colours. The community knows these caveats, but JWST raises the stakes. The most extreme candidates are also the most vulnerable to exotic contaminants, because the data are pushed to limits where small effects matter. A single, misclassified object can ripple through headlines, even if the statistics are eventually corrected. So the hunt becomes a game of additional ingredients. If colours can be faked, then we need tests that do not depend on colour alone, tests that are orthogonal to the spectral cliff. The goal is not to abandon the method, but to harden it against the new kinds of confusion JWST makes possible. One ingredient is morphology, but it is limited. At JWST resolution, a very distant galaxy can look nearly point-like, especially when faint and lensed, and a nearby brown dwarf is also point-like. You can measure shape, but at the edge of detection, the shape is mostly the point spread function. Another ingredient is lensing geometry, but it is not decisive. A true background galaxy might be magnified in a way consistent with the cluster's mass model, and it might have counter-images in predictable places. But a nearby object can still sit in a lensing field by coincidence, because the lens does not affect it at all. Another ingredient is spectroscopy, but it is expensive and sometimes impossible. The faintest candidates can be beyond practical spectral confirmation, even for JWST, because spectra require more photons than imaging. When the object is barely detected in a few bands, dispersing its light can erase it, so the team looks for a test that is cheap in photons and ruthless in logic. They look for something the edge of the universe cannot imitate, something that does not care about templates or priors. They look for a property that divides nearby from distant by geometry alone. A galaxy at redshift 15 should not move against the background on human timescales. Its proper motion across the sky should be effectively zero, because it is unimaginably far away and its angular shift is vanishing. Even if it is racing through space, distance makes the motion negligible. A nearby object in the Milky Way can move measurably in a year. Its parallax and proper motion can shift its position by tiny but detectable amounts, especially with a stable space telescope and careful astrometry. The motion may be subtle, but it is real, and it accumulates. Parallax is the simplest geometry, the apparent shift caused by Earth's orbit around the Sun. Proper motion is the object's own drift through space, projected onto the sky. Together they create a signature that no distant galaxy can replicate, because the baseline of our orbit is too small compared to cosmic distances. In practice, the shifts are measured in fractions of an arc-second, sometimes far smaller than a pixel. That is why calibration becomes part of the drama, because you must know the camera's distortions and the field's reference points. If the dots move relative to distant galaxies that should be fixed, the conclusion is hard to escape. This is the pivot hidden inside the mystery. The dots look like textbook high redshift dropouts, until motion enters the story and motion changes the rules. Suddenly the question is not only what wavelengths they emit, but where they are located in space. And motion is not a matter of interpretation. Motion is a geometric fact that turns a cosmic claim into a local one, if the shift is real. If the dots drift between epochs, then they are not at the edge of the universe, no matter how perfect their colours appear. So Chapter 2 ends with the method laid bare, both its elegance and its vulnerability. We have a toolkit that usually works, and a telescope that makes its rare failures more instructive, because it pushes into regimes where imposters become visible. The same breakthrough that reveals the first galaxies also reveals new ways to be fooled. Next, the same field is observed again, and the dots are compared frame to frame. The investigation stops asking what their colours mean, and starts asking whether they drift. In that comparison, pixel to pixel, epoch to epoch, the universe must either stand still or give itself away. The fastest way to test a miracle is to let time touch it, because time is the one variable a false signal cannot negotiate with. The team chooses the slow test, because the slow test is the clean one, an experiment written in geometry rather than hope. In astronomy, where light can travel for billions of years, a single year sounds small, yet it can still separate the local from the truly distant. In the first epoch, the two red dots sit exactly where the pipeline found them, isolated and quiet in a crowded lensing field. They look almost too neat, two pinpricks of infrared light tucked among warped arcs and smeared galaxies. The surrounding scene is busy, full of gravitationally stretched shapes, yet these 2 points remain compact, as if they refuse to be pulled into the cluster's visual chaos. In the second epoch, the question is brutally simple, and it is asked with no room for interpretation. Do they stay put against the deep background, or do they drift? The entire claim, with all its cosmic implications, collapses into a measurement of position, an answer written in fractions of a pixel. A year sounds like patience, But it is also a baseline that astronomy has trusted for centuries. It is the length of Earth's orbit, and it is the rhythm of parallax, repeated with the reliability of a metronome. It is long enough for nearby objects to reveal motion, and short enough that the distant universe stays fixed. It is also long enough for instrumental quirks to be retested, because a second visit forces the analysis to survive repetition. This is why waiting is not passive in observational astronomy. Even when the telescope appears to be doing nothing, waiting is a measurement strategy built from geometry and repetition, and it turns the sky into a controlled laboratory. The photons arrive when they arrive, but the baseline is chosen, and the baseline is what makes the test decisive. If the dots are background galaxies, they should be stationary on human timescales, even in a field distorted by gravitational lensing. Their angular motion would be effectively zero, even if their true velocities are enormous in physical space. Distance crushes motion into invisibility, because the same transverse speed subtends a smaller angle when the object is unimaginably far. A galaxy can race through space and still appear nailed to the sky, because the sky is measured in angles, not in kilometers. If the dots are in the Milky Way, they should move, and they should do so in a way that is hard to hide. They orbit the galaxy with the Sun, and they carry their own peculiar velocities layered on top of the disk's rotation. Their apparent positions should shift against the far background, because nearby things cannot escape astrometry. Even a faint object barely above the noise can betray itself if it slides consistently relative to the distant grid. The team frames the year as a fork in the story, and the fork has consequences that reach beyond one dataset. One branch leads to the first galaxies in a rewritten timeline, where structure forms earlier than expected. The other branch leads to a local population we did not expect to find here, hiding in the same colour space. Either way, the result is not merely a label for two dots, because it changes what the search method can safely claim. Proper motion is the first concept that makes the fork real, because it is motion that accumulates steadily rather than oscillating. It is the drift of a nearby object across the sky, caused by its velocity through space relative to the Sun. It is measured as an angular rate, usually in milliseconds per year, which sounds tiny until you remember how precise modern imaging has become. In the era of space telescopes, a millisecond is no longer an abstraction, because it is something an instrument can actually chase. On a star chart, proper motion looks like sideways crawling, a slow slide across a backdrop that hardly changes. The object changes its right ascension and declination, while the background galaxies form a nearly rigid grid. The grid is not perfectly rigid, but its residual motions are so small that they function as a fixed reference. When the reference is built from thousands of distant sources, the average becomes stable, and stability is what makes motion visible. The physical cause is ordinary, and that is the point, because ordinary physics is the best tool for dismantling extraordinary claims. Stars and substellar objects orbit the Milky Way, and their orbits are not synchronized with ours. Over months and years, the difference accumulates into a measurable shift, like watching a nearby car drift against distant mountains. The analogy is almost embarrassingly simple, yet it captures the essence of astrometry. Near things shift more than far things. Typical proper motions depend on distance and transverse velocity, and the relationship is simple in plain language. The closer the object, the larger the angular motion for the same speed, because the same path spans more sky. A nearby object at tens of parsecs can move tens to hundreds of milliseconds per year, and even a more distant halo object can move enough for JWST to detect. At those scales, a single year can turn a static photograph into a short, silent movie. There is also a historical echo here, because proper motion is one of the oldest proofs that the sky is not immutable. In the early 18th century, Edmund Halley compared ancient star positions to modern ones, and discovered that some stars had shifted. The fixed stars were not fixed after all, and the universe became a place of motion rather than a painted dome. That realization was not just technical, it was philosophical, because it replaced permanence with dynamics. Later, as astrometry matured, proper motion became a way to map the Milky Way's structure and kinematics. It helped identify nearby stars, high-velocity halo objects, and members of moving groups that share a common origin. In other words, a tiny drift on the sky became a fingerprint of where an object belongs. The team leans on that tradition now, because the same measurement that once humbled the idea of fixed stars can also humble a modern claim of cosmic dawn. The second concept is parallax, and parallax is pure geometry, the kind that does not care what you want to be true. As Earth goes around the Sun, our viewpoint changes by 2 astronomical units peak to peak. Nearby objects appear to shift back and forth relative to the distant background, tracing a small annual wobble. It is a subtle dance, but it repeats with the calendar, and repetition is what turns a wobble into a distance. Parallax is not the object moving through space, and that distinction matters when you later interpret the vector. It is the observer moving, and the sky responding like a depth cue, the same way your thumb seems to jump when you close one eye. The motion is apparent, but it is measurable, and it carries distance information directly. In practice, the observed track can be a combination of steady proper motion and the annual parallax loop, 2 motions layered into one curve. The parallax amplitude is inversely proportional to distance, and that inverse relationship is the backbone of the cosmic distance ladder. 1 parsec corresponds to 1 arcsecond of annual parallax by definition, a unit invented to match the geometry. At 10 parsecs, the parallax is 1/10 of an arcsecond, and at 100 parsecs it is 10 milliseconds. Those numbers are small, yet they are large enough to matter when your camera can measure centroids with exquisite precision. For galaxies billions of light years away, parallax is essentially 0, because the baseline becomes negligible compared to the distance. The diameter of Earth's orbit is huge by human standards, yet microscopic against cosmological scales. The apparent shift collapses below any realistic measurement, even with exquisite instruments. A cosmological source can flicker, brighten, or fade, but it does not wobble with the seasons. JWST complicates and improves this geometry at the same time, because it does not orbit Earth and it does not sit on the ground. It orbits the Sun near the Earth, Sun L2 point, trailing Earth while sharing a similar annual path. From that vantage, it sees a colder, darker sky, and it also sees the field from a slightly different place. The telescope's thermal stability helps photometry, and its stable pointing helps astrometry, but neither removes the need for careful geometric accounting. That means JWST still samples a changing vantage point across the year, and the parallax signal is still present. The baseline is still of order an astronomical unit, though the exact geometry depends on JWST's halo orbit around L2. The details differ, but the logic remains ruthless. Nearby things wobble, distant things do not. If a source shifts in a way that matches the annual rhythm, the sky's telling you it is close, so the plan becomes concrete, and it has the satisfying simplicity of a well-posed experiment. Re-observe the bullet cluster field after roughly 1 year, using comparable filters and exposure depth. Measure the positions of the 2 dots again, and compare them to the first epoch. The goal is not to make a prettier picture, but to force the claim to survive a second independent snapshot. The comparison sounds simple, but the measurement is not, because the shifts live in the regime where imperfections become characters in the story. The motions are tiny, and the camera is not a perfect grid, even when its behavior is well calibrated. The team must turn 2 deep images into a single coordinate system with errors smaller than the motion they seek. In that regime, every assumption has a price, and every calibration step must be justified. Astrometry begins with alignment, and alignment begins with reference points that behave like nails in the sky. In this field, the best reference points are distant galaxies, because they are effectively fixed over a year. There are many of them, scattered across the frame like faint irregular islands of light. Some are compact enough to act like points, while others are messy, and the team must choose carefully. The team selects a set of compact high signal-to-noise galaxies across the frame, because compact sources yield more stable centroids. They avoid saturated stars, which can have bleeding and nonlinear pixels, and they avoid extended cluster members with messy centroids. They build a reference catalogue that can anchor both epochs, and they treat it like a scaffold. The scaffold must be wide, because a transformation constrained only near the centre can fail at the edges. Then they confront distortion, because every camera distorts, and distortion is the quiet enemy of precision. NearCam has a well-characterised geometric distortion, mapped through calibration programs and repeated checks, yet it must be applied correctly, because small residuals can masquerade as motion if left uncorrected. A distortion pattern that is stable but misapplied can create a false drift, and that is exactly what the team is trying to avoid. They apply the instrument distortion solution and check it against the data, looking for patterns that would betray a systematic error. They use the dither pattern to sample different detector pixels, because dithering averages over pixel-to-pixel sensitivity variations. They verify that the reference galaxies land consistently after correction, rather than drifting in a coherent way. In a good alignment, the residuals look like scatter, not like a directional flow. They also correct for rotation and scale differences between epochs, because JWST's pointing and roll angle can change between visits. The field can be observed with slightly different orientations, and the mapping from detector coordinates to sky coordinates must account for that. A small rotation error across a wide field can create apparent shifts that grow with distance from the centre. That kind of error is seductive because it can look like a real motion for objects far from the pivot point. The team fits a transformation between the two epochs using the reference galaxies, and the fit is both mathematical and visual. The transformation includes translation, rotation, and scale, and sometimes higher order terms to capture subtle warps. The goal is to make the background grid overlap as tightly as possible, until the galaxies stack like a single exposure. When it works, the field stops looking like two images and starts looking like one, with time hidden inside it. Only after the grid is locked do they measure the dots, because measuring early would bake alignment errors into the result. They centroid each dot in each epoch, using the point spread function as a model rather than a simple brightness peak. They propagate uncertainties from photon noise, background subtraction, and PSF mismatch, because each of those terms can bias a faint centroid. In deep infrared imaging, the PSF is structured, and even small mismatches can shift a fitted position. Now the units matter, because the detector speaks in pixels, and pixels are not angles until you calibrate them. A pixel shift must be converted into an angle on the sky, and the conversion depends on the plate scale. JWST's plate scale is known, but the effective scale depends on distortion correction and the exact filter, so the team treats it with care. A mistake of a fraction of a percent can matter when the signal is measured in milliseconds. They translate pixel offsets into milliseconds, which is the language of astrometry and the scale of the expected signal. They compute a motion vector for each dot, with an uncertainty ellipse that captures correlated errors. They ask whether the vector is consistent with zero, or whether it is decisively non-zero, and they let statistics make the call. The ellipse is not just decoration. It is the honest shape of the uncertainty, stretched by the geometry of the measurement. They also run sanity checks that are designed to kill wishful thinking, because the human mind is skilled at seeing what it hopes for. They measure other faint sources that should be stationary, to confirm the residual frame-to-frame scatter after alignment. They test whether the measured motion depends on centroiding method or reference selection, because a fragile result is not a result. If a motion disappears when you change a reasonable choice, it was never a motion in the first place. They check whether the dots could be affected by blending or background gradients, which are common in a lensing field full of diffuse light. Light from cluster galaxies can bias centroids, especially when a faint point source sits on a shallow slope of starlight. A small residual from subtraction can pull a faint point source in a consistent direction, creating a false vector. In crowded fields, the background is not a flat canvas, and the team must model it like terrain. They repeat the measurement with different local background models, and they do it systematically rather than once. They mask nearby structures and refit the centroids, changing apertures and fitting radii to see what moves. They confirm that the motion persists across reasonable choices, which is the hallmark of a real signal. When the arrow survives every attempt to erase it, it stops being a suggestion and becomes a fact. The year of waiting becomes a plot, and the plot has arrows that are hard to unsee once drawn. Both red dots shift sideways across the sky between epochs, and the shift is small but coherent. It is statistically significant, and it points in a direction that does not match random noise. In an overlay, the background galaxies snap into place, while the dots sit slightly off their former positions, like footprints that no longer match the shoes. This is the decisive result of the chapter, delivered not by a spectacular image, but by a measured displacement. The dots do not sit still like distant galaxies. They move like nearby objects, and the sky itself becomes the witness. The experiment does not ask what the dots look like, because looks can be deceiving, and it asks only where they are. The direction matters, because random errors do not produce consistent vectors that survive multiple analysis choices. The magnitude matters, because it is too large to be explained by residual distortion alone, given the behavior of the reference grid. The motion is not a subtle preference in a probability distribution, and it is not a fragile signal at the edge of detectability. It is a measured displacement, the kind that forces a reclassification even when you do not want one. At this moment, the edge of the universe moves, and the movement is not out there but in our interpretation. The claim of a record-breaking galaxy does not survive a geometric test, because geometry is indifferent to narrative. A year of baseline, a careful alignment, and a few milliseconds are enough to puncture a story that felt almost inevitable. A galaxy at redshift 15 cannot show measurable proper motion over 1 year, not in any realistic physical scenario. Even if it were moving at thousands of kilometers per second, its angular motion would be immeasurably small. The distance makes the sky rigid, turning real velocities into vanishing angles. The farther the source, the more the universe turns motion into stillness, at least from our vantage. Parallax is even more unforgiving, because it's tied directly to the observer's orbit rather than the object's own motion. A background galaxy has effectively zero annual parallax, because the baseline is trivial compared to the distance. If the dots show an annual shift pattern, they must be nearby, and the word nearby becomes unavoidable. The wobble is not a matter of interpretation, because the geometry is fixed by the size of the orbit. The team considers whether lensing could rescue the original interpretation, because lensing is the reason the field was chosen in the first place. Lensing can magnify and distort, and it can create multiple images that mimic strange morphologies. Lensing can also shift apparent positions relative to unlensed coordinates, because it bends light paths through curved space-time. In a single epoch, lensing can make the sky look like a hall of mirrors. But lensing cannot make a background galaxy appear to move across the sky between epochs, at least not at the millisecond level on a 1-year baseline. The lensing mass distribution does not change enough in a year to create such shifts, because clusters evolve on far longer timescales. The cluster is massive, but it is not rearranging itself on human timescales. Even the internal motions of galaxies within the cluster are too small, in angular terms, to mimic a nearby object's drift. A lens can change how we map image plane to source plane, and it can complicate where an object appears in a single exposure. It cannot create time-dependent astrometric motion that tracks our changing viewpoint, because the gravitational potential is effectively static across a year. Lensing is static geometry, not a moving reference frame. If anything changes quickly, it is our perspective, and that is exactly what parallax exploits. The only way a background galaxy could appear to move is if the reference frame itself moved, and that possibility is examined carefully. But the reference frame is built from many distant galaxies, and they do not share a coherent drift across the detector. The grid stays put while the dots slide, and that contrast is exactly what astrometry is designed to reveal. The measurement is differential, and differential measurements are hard to fool when the reference is abundant. So the extraordinary claim collapses into a different kind of wonder, the kind that lives closer to home. The dots are not messages from the first 200 million years, and they are not the earliest cities of stars. They are visitors from our own galactic neighbourhood, faint enough to hide in plain sight, and red enough to masquerade as cosmic dawn. The universe did not give us the earliest galaxy, but it did give us a lesson in how easily the nearby can imitate the far. This is not a failure of JWST's sensitivity, and it is not a cautionary tale about overreach alone. It is a demonstration of what sensitivity makes possible, because deeper vision expands both discovery and confusion. When you can see faint infrared points anywhere, you will sometimes find the Milky Way in the middle of a cosmology field. The telescope is doing what it was built to do, revealing what was previously invisible, even when that invisibility was local. There is a quiet irony in that, and it has precedent in the history of sky surveys. Astronomers have repeatedly built instruments to look far away, only to discover unexpected populations nearby. The same sensitivity that reveals the distant universe also exposes the faint tail of local objects, and those locals can imitate the distant in broad strokes. When you push to the limits, the universe answers with edge cases, and edge cases are where classifications break. The team now has a new problem, and it is sharper than before, because it attacks the method rather than the conclusion. If the dots are nearby, why did every high redshift test say they were ancient? Why did the dropout signature look so clean, so textbook, so persuasive? The discomfort is not that the claim was wrong, but that the data looked right while pointing to the wrong place. The answer must live in the spectrum, because the colours were the disguise, and colour is a compressed form of spectroscopy. Broadband filters are blunt instruments, yet they encode the shape of the underlying spectral energy distribution. If two different physical mechanisms create similar breaks across those filters, photometry alone can be trapped. The trap is not a bug in the detector, but a degeneracy in how nature can sculpt light. The same filters that map hydrogen absorption at the dawn of galaxies can also map molecular absorption in cold atmospheres, and that overlap is the trapdoor. In the early universe, neutral hydrogen absorbs ultraviolet photons shortward of the Lyman limit, and the intergalactic medium deepens that suppression. As expansion stretches light to longer wavelengths, that cliff slides into the infrared, right where JWST is most sensitive. The dropout technique is powerful, precisely because the cliff is so sharp, but sharpness can be forged by other physics. The chapter turns toward that coincidence, because coincidence is where astronomy gets dangerous and interesting at the same time. Hydrogen in the early universe creates a cliff in ultraviolet light, shifted into infrared by expansion, and the cliff can look abrupt in broad bands. Methane in a cold atmosphere creates a cliff in infrared light, carved by chemistry, and it can be just as abrupt. Two different universes, one cosmological, one local, can draw the same silhouette. In a cold brown dwarf or a planetary mass object, molecules do not merely tint the spectrum, they sculpt it with deep absorption bands. Methane absorbs strongly in the near-infrared, and water vapour adds its own broad troughs. Collision-induced absorption from molecular hydrogen can further suppress parts of the spectrum, especially in dense, cool atmospheres. The result can be a spectrum that rises and falls sharply across the same filter boundaries used to identify high redshift dropouts. In broadband photometry, a cliff is a cliff, and the detector does not label its cause. A pipeline can be fooled if the template library is incomplete, or if the data are too sparse to break degeneracies. A perfect dropout can be a perfect imposter, especially when the object is faint and the uncertainties widen the allowed solutions. When the signal-to-noise drops, the parameter space opens, and the most dramatic explanation can win by default. There is also a subtle statistical pressure in any search for extremes, because the rarest objects are sought at the limits of detection. Near the limit, noise can scatter ordinary sources into extraordinary-looking colours, and selection cuts can amplify that effect. The team knows this, which is why they needed a test that does not rely on colour alone. Time, unlike colour, does not care how convincing a spectral break appears. The year of waiting did what photometry alone could not do, and it did it with an elegance that feels almost old-fashioned. It used the sky as a detector, and it used time as an instrument, and it demanded consistency across epochs. It separated distant from nearby with geometry rather than interpretation, and geometry does not care about templates. In a field built to magnify the early universe, the most decisive tool turned out to be the calendar. Now the story pivots again, because motion answers where they are, not what they are, and location is only the first half of identity. A moving point source could be a cool brown dwarf, a free-floating planetary mass object, or something even rarer in the galactic halo. Each possibility carries a different formation story, and each would explain the redness in a different way. The motion is a door that closes on one explanation, while opening several others. The team prepares to ask the next question with the right tool, because the new hypothesis implies a new diagnostic. If the dots are local, their spectra should show molecular bands, not a redshifted Lyman break. The disguise should have a chemical signature, written in absorption features rather than in a single dramatic drop. A spectrum can reveal whether the cliff is carved by hydrogen in intergalactic space or by methane in a cold atmosphere. The transition is unavoidable because the mystery has changed shape, and the next step must match the new shape. The dots are not at the edge of the universe, yet they wore the edge's colours perfectly, and that is not an accident. The next chapter follows the spectral coincidence that made the mistake plausible, and it treats the coincidence as a clue rather than an embarrassment. In science, the most valuable errors are the ones that expose a hidden assumption. Hydrogen wrote the original story in our minds because cosmic dawn is one of the great frontiers of modern astronomy. Methane may have written the same pattern in the data because cold atmospheres are chemical laboratories that can mimic cosmological signatures. The same filters, the same colours, and two radically different distances. How often does the universe offer such a clean illusion? When it does, it forces a question that is both technical and philosophical. What else might our methods be quietly mislabeling? And the central question tightens rather than dissolves, because the revelation raises a more intimate kind of uncertainty. If those two faint red dots were not galaxies from the first 200 million years, what were they? What does their disguise reveal about how we search for cosmic dawn, and what else might be hiding in the same blind spot? The year of waiting has answered one question with motion, and it has set the next question loose in the spectrum. The red dots were never imaginary. The detections were real, repeatable and stubbornly point-like in JWST's deepest frames. In the stacked images, they sat like pinpricks on velvet. No spiral arms, no fuzzy halos, just compact light at the edge of the noise. That stubbornness mattered, because deep field astronomy is built on skepticism. Cosmic rays, hot pixels, diffraction spikes and imperfect background subtraction all leave ghosts. Yet these sources returned night after night in independent reductions. The telescope's optics, its segmented mirror and crisp point spread function, made the dots look clean, and that cleanliness encouraged belief. What changed was the meaning of their redness. Red can mean distance, but red can also mean temperature and chemistry. In astronomy, red is not a paint colour. It is a bookkeeping system for where photons land in wavelength. A source can look red because space stretched its light. A source can also look red because it emits most strongly at longer wavelengths, like a warm stove glowing in infrared. And a source can look red because molecules in its atmosphere swallow certain colours, leaving only a few bright windows. Chapter 3 used time to break the spell. Motion said the sources were nearby, yet the colours still looked like cosmic dawn. Proper motion is a simple test with a profound implication. Nearby objects shift against the background as Earth and the telescope change vantage. In the JWST images, the dots slid by tiny fractions of an arc-second. That shift was small enough to miss at first glance, yet large enough to be incompatible with galaxies billions of light-years away. The universe can expand, galaxies can merge, but distant galaxies do not drift across the sky on human timescales. So the mystery reframes itself. The question is no longer whether the dots exist, but how they borrowed a high-Z disguise. The disguise is not a lie in the data, it is an ambiguity in how we translate data into distance. That ambiguity begins with a simple fact about imaging. Broadband filters do not see a spectrum, they see weighted averages. A camera does not read a barcode of wavelengths. It collects photons through a coloured window and reports one number. A filter measurement is a single number that compresses many wavelengths into one brightness. That compression creates room for coincidences. When different physical processes remove light in different places, the averaging can hide the difference. Dropout selection depends on a sharp cliff. If flux collapses in one band and returns in the next, distance feels inevitable. The method is elegant because it turns a complex spectrum into a simple yes or no pattern. At cosmic dawn, the cliff is hydrogen. In our neighbourhood, the cliff can be methane. The same cliff-like pattern can be produced by very different physics, and the filters do not announce which physics did the carving. The Lyman break is a physical shutoff in the rest frame ultraviolet. Neutral hydrogen wipes out photons shortward of Lyman alpha and the Lyman limit. In plain terms, hydrogen atoms are extremely good at intercepting ultraviolet light at specific energies. In the early universe, the intergalactic medium deepens that suppression. Rionization is incomplete, so the blue side is chewed away. Between young galaxies, vast reservoirs of neutral gas act like fog, turning ultraviolet into absence. Cosmic expansion then moves that missing ultraviolet into the near-infrared. The break slides through JWST's NIRCam filters as redshift rises. A photon that began in the ultraviolet can arrive stretched into infrared, carrying the signature of what was removed along the way. In filter space, this becomes a clean dropout. The source is absent in shorter bands, then suddenly present in longer ones. The transition can be so steep that it looks like a step function, especially when the object is faint. That logic is why the red dots looked so persuasive. Their non-detections lined up with where a Lyman break should land. In colour plots, they sat in the same corner where the earliest galaxies are expected to gather. There is history behind that confidence. The dropout technique helped map galaxies when the Hubble Space Telescope pushed into the deep fields, and it became a workhorse for studying the young universe. JWST inherited that tradition, but it also inherited the method's vulnerabilities. But a second physics process can carve a similar gap. It happens in atmospheres that are cold, dense, and molecule-rich. Instead of intergalactic hydrogen erasing ultraviolet, local molecules erase near-infrared bands. Ultra-cool substellar objects live at hundreds of Kelvin, not thousands. Their light is thermal, and their spectra are heavily sculpted. They do not shine like stars powered by fusion, they glow like cooling embers. As temperatures fall, chemistry changes what survives in the gas phase. Carbon shifts into methane, and oxygen favours water vapour. These are equilibrium tendencies. Given enough time, atoms settle into the molecules that are most stable at that temperature and pressure. Methane absorption is not a minor tint. CH4 produces deep bands in the near-infrared that can erase broad chunks of flux. The molecule has vibrational modes that resonate with infrared photons, and those resonances create wide, dark troughs. Water vapour adds its own wide troughs. H2O absorption overlaps key near-infrared windows and reshapes the continuum into peaks. Where the atmosphere is transparent, light escapes. Where it is opaque, the spectrum collapses. Collision-induced absorption from H2 can further suppress flux. In dense atmospheres, even molecules without permanent dipoles can darken the spectrum. When hydrogen molecules collide, they briefly become able to absorb infrared light, and the effect grows with pressure. The result is a jagged spectral energy distribution. Brightness rises in relatively transparent windows, then collapses where molecules bite. It is not a smooth slope, it is a landscape of ridges and valleys. A galaxy spectrum at high redshift can also look jagged in filters. The jaggedness comes from a break plus lines and noise. Strong emission lines can brighten one band, while the Lyman break empties another, and faintness makes every point uncertain. This is the optical illusion at the heart of the story. Two different universes can draw the same silhouette in broad bands. One universe is the first billion years after the Big Bang, and the other is the cold outskirts of our own galaxy. To understand the illusion, the chapter slows down to filter intuition. The trick is not one filter, but the gaps between them. Filters are not continuous coverage. They are discrete windows separated by boundaries where the spectrum is unsampled. Each NIRCam filter samples a wide wavelength range. If a trough sits inside one filter, that whole measurement can drop. The detector does not know the trough is narrow or wide, it simply counts fewer photons. If the next filter lands on a transmission peak, the object reappears. The pattern looks like a cliff, even when it is not. In the image, that reappearance can feel dramatic. One band shows nothing, the next shows a crisp point. For a Lyman break galaxy, the missing light is removed by intergalactic hydrogen. For a methane object, the missing light is removed locally. The first is a cosmological curtain, the second is an atmospheric mask. The detector records the same outcome either way. One band is quiet, the next band is loud, and the pipeline calls it a dropout. The algorithm is doing what it was designed to do, yet it cannot see the difference between causes. This is why methane can mimic a high Z selection box. The colour jump can be steep enough to satisfy strict cuts. A deep methane band can create a red colour index that looks like an extreme redshift. The mimicry is strongest when the trough aligns with a specific filter boundary. Small shifts in temperature can move the peaks and troughs. In ultra-cool atmospheres, a change of tens of Kelvin can subtly reshape the balance between methane, water, and pressure effects. That sensitivity makes the imposters rare but dangerous. A small local population can land precisely where the high Z box lives. Most nearby objects will not match the exact colour criteria, but a few will thread the needle. The red dots were faint, and faintness amplifies every degeneracy. When uncertainties grow, more templates become acceptable. A measurement with large error bars can be consistent with multiple physical scenarios, even if one is unlikely. Photometric redshift fitting is powerful, but it is not magic. It compares coarse filter points to libraries that can never be complete. The code searches for the best match among what it has been given, not among everything nature can produce. If the library underrepresents ultra-cool atmospheres, the code tries to explain a methane trough as a Lyman break. It can prefer extreme redshift. The fit is not malicious, it is constrained by the menu of possibilities. Even with stellar templates included, the fit can be unstable. Low signal to noise in the decisive bands widens the probability peaks. The redshift likelihood can develop multiple islands, one at high redshift, another at low redshift. separated by uncertainty. A non-detection is not a number, it is a limit. Limits can be misestimated when backgrounds are complex and sources are near the threshold. What looks like zero flux is often flux below what we can confidently separate from noise. In deep fields, the background is never perfectly flat. Small errors in subtraction can push a marginal detection below the cutoff. The infrared sky has structure, zodiacal light, scattered light, and detector systematics that must be modelled and removed. That is not fraud, it is statistics. The same data that reveal faint sources also create more ways to mismeasure them. When you hunt at the edge of detectability, you live in a world where small biases matter. The bullet cluster adds another pressure. Lensing makes distant galaxies brighter, but it also changes what we choose to follow up. The cluster's mass bends space-time, creating magnification patterns that can turn the almost impossible into the barely visible. Magnification biases us toward the most extreme-looking objects. The more dramatic the colour break, the more attention it receives. In practice, follow-up time is limited, and observers naturally prioritise the most compelling candidates. Deep lensing fields also amplify the impact of contaminants. When you search a tiny area to extreme depth, rare locals can matter. The survey volume for nearby objects is small, yet the selection is so sharp that a few interlopers can dominate. A handful of nearby cold objects can slip into the sample. They are not common, but they do not need to be common. A single ultra-cool object with the right spectral troughs can masquerade as a galaxy from the first era. They only need to be convincing. In a dataset designed to find the earliest galaxies, a single perfect imposter can dominate the narrative. The human mind is drawn to the outlier because the outlier promises a new chapter of cosmic history. Dust complicates the picture without being the main culprit. Dust can redden a spectrum smoothly, and smooth slopes can masquerade as breaks in noisy data. Dust grains scatter and absorb blue light more efficiently, tilting the spectrum toward the red. Dust also interacts with lensing selection. A dusty moderate Z galaxy can be boosted into detectability and then misfit at high redshift. If the key blue bands are weak and the red bands are magnified, the photometry can drift into the dropout region. So the chapter draws a boundary. Not every red source is methane, and not every dropout is hydrogen. The sky contains a spectrum of possibilities, and the goal is to separate them without flattening the mystery. The point is that the filter-level evidence is ambiguous at the limit. When sources are faint, broadband photometry can be a hall of mirrors. Each filter becomes a reflection that depends on noise, background, and the hidden shape of the true spectrum. This is the emotional pivot of the series. The edge of the universe did not vanish, but it was briefly shared. The red dots did not erase cosmic dawn. They reminded us that discovery often begins with confusion. For a moment, cosmic dawn and a cold neighbour occupied the same colours. The overlap was not poetic, it was instrumental. The instrument's filters were never designed to distinguish every astrophysical imposter at the faintest levels. That overlap does not embarrass the search. It reveals where the search is fragile and why additional tests are non-negotiable. A method can be brilliant and still have failure modes, especially when pushed beyond its original regime. The community's first defense is to widen the filter set. More bands can sample the shape of the spectrum beyond a single cliff. With enough sampling, a jagged methane spectrum reveals itself as multiple dips rather than one clean break. A methane object does not produce a single break and then a flat red continuum. It produces multiple troughs that can be caught with the right filters. If you measure across several near-infrared bands, the pattern becomes harder to fake. A high Z galaxy should show a consistent red side slope. Its continuum redwood of the break is shaped by stars and dust, not deep molecular bands. The slope may be blue or red depending on dust, but it should not oscillate sharply from band to band. But even that distinction can blur when the object is faint. At low signal to noise, a multi-trough spectrum can look like a single break. Noise can fill in a trough or deepen a peak, and the true shape becomes uncertain. The next defense is to improve template libraries and priors. If ultra-cool populations are missing, the algorithm cannot choose them. Template sets must reflect the diversity of substellar atmospheres, including variations in gravity, metallicity, and cloud structure. Those variations matter because they move the spectral windows. Lower gravity can broaden features, while metallicity can change molecular abundances and opacities. A template library that ignores these knobs can misclassify real objects. Priors matter because extreme redshifts are rare. Without a realistic prior, a slight likelihood advantage can push the fit to the edge. When two solutions fit similarly well, the prior is the tiebreaker that encodes what is plausible. Yet priors can also hide surprises. If the universe produces an early galaxy outside expectations, a strong prior can downweight it. The history of astronomy includes many cases where the improbable became real once instruments improved. So the chapter emphasizes balance. We need priors that prevent obvious mistakes, but not priors that forbid discovery. The goal is disciplined openness, skeptical enough to avoid mirages, flexible enough to recognize the unprecedented. Another defense is to use morphology carefully. Point-like does not mean local, because the earliest galaxies can be compact and lensed. At high redshift, galaxies can be physically small, and lensing can further compress their apparent size. Still, morphology can whisper clues. A nearby object should match the telescope's point spread function closely, while a lensed galaxy may show slight elongation or asymmetry. These are subtle differences, and they require high signal-to-noise to trust. Another defense is to use lensing geometry. A true background galaxy might have counter-images or align with critical curves, but models have uncertainties. The bullet cluster's mass distribution is complex, and small modelling differences can shift predicted image positions. The decisive defense remains orthogonal to colour. Motion and spectroscopy do not ask the same question as photometry. Photometry asks, what is the average brightness in each window, while spectroscopy asks, where exactly is the light missing? Motion answered where the red dots are. Spectroscopy must answer what carved their missing light. The same colours can come from different mechanisms, but the detailed spectrum carries a fingerprint. If methane is responsible, the spectrum should show recognisable absorption bands. The pattern should repeat across wavelengths, not just at one boundary. Methane and water create a sequence of troughs that line up with known molecular transitions. In a spectrum, those troughs are not arbitrary. They have characteristic widths and depths, shaped by pressure broadening and temperature-dependent chemistry. Seeing them in the right places is like hearing a familiar chord progression. If hydrogen at cosmic dawn were responsible, the spectrum would show a break consistent with red-shifted ultraviolet suppression. The red side would behave differently. Instead of multiple molecular valleys, you would expect a relatively smooth continuum punctuated by emission lines. Those lines matter because early galaxies can have strong nebular emission. Ionized gas around young stars can brighten specific wavelengths, and those brightenings can distort broadband colours. Spectroscopy can separate a true continuum break from line-driven tricks. This is why the chapter calls it a spectral coincidence. The same filter gaps can be produced by cosmic hydrogen or local methane. The coincidence is not mystical. It is the predictable outcome of sampling complex spectra with broad windows. The coincidence is not a fluke of one dataset. It is a structural risk whenever near-infrared dropouts are pushed to extreme depth. The deeper we go, the more we invite rare objects, and the more we rely on limits rather than measurements. JWST makes that risk visible because it is sensitive to both regimes. It reaches early galaxies and it reaches cold wanderers. Its infrared vision is precisely what you need to see the first starlight, and it is also what you need to see a cooling atmosphere nearby. The red dots therefore become a lesson, not a punchline. They show that the outskirts of our galaxy overlap the edge of cosmic time in colour space. The map of the early universe, it turns out, shares symbols with the map of our local neighbourhood. The chapter returns to the central question with sharper edges. If the dots were not first galaxies, what were they, and how many more hide similarly? How many candidates in future deep fields will sit on that same knife edge of interpretation? The answer will live in classification. We must decide whether the culprits are stars, planets, or objects in between. Substellar objects blur categories because they can form like stars yet cool like planets. The transition is unavoidable because the mystery has changed shape. If the culprits are local, we need to name them and explain their origin. That means confronting the physics of ultra-cool atmospheres, their formation pathways, and their place in the Milky Way. Next, we follow the evidence from colours to physical identity. The search for cosmic dawn becomes a search through the Milky Way's coldest shadows, and in those shadows the same infrared photons that once promised the first galaxies may reveal a different frontier entirely. Expanded section. Continued narration. To appreciate why the disguise worked so well, It helps to picture the data the way the instrument sees it. NIRCam does not deliver a rainbow, it delivers a small set of snapshots, each one taken through a different filter. Those filters have names like F290W or F150W, but in practice they are broad windows with gently sloping edges. When astronomers speak about colours in this context, they mean differences between those snapshots. A colour is not a property of the object alone, it is a comparison between two filter measurements. That comparison can be dominated by a single absorption trough if the trough sits in one window and not the other. In the early universe, the Lyman break is powerful because it is abrupt in the rest frame. Neutral hydrogen has a sharp threshold for absorbing ultraviolet photons, and the intergalactic medium adds a forest of absorption lines. Together they create a steep drop that can look like a cliff even after being blurred by a broad filter. The physical reason is simple, even if the details are not. Hydrogen atoms absorb photons energetic enough to excite electrons from the ground state, and photons above the Lyman limit are readily removed. When the universe is filled with neutral hydrogen, those photons rarely travel far. Ionization changes that story gradually. As the first stars and galaxies ignite, their ultraviolet radiation ionizes the surrounding gas, turning neutral hydrogen into plasma. Yet reionization is patchy, and along many lines of sight the ultraviolet is still suppressed. So a galaxy at very high redshift can appear to turn on only in redder filters. The bluer filters are sampling wavelengths that, in the galaxy's rest frame, fall below Lyman alpha. The photons were either never received or were absorbed along the way. That is the logic that built the selection boxes. It is also the logic that has delivered real discoveries, from the first Hubble Deep Field dropouts to the earliest JWST candidates. The method works because the universe provides a real, repeatable spectral feature. But methane provides something that is repeatable too. In a cold atmosphere, methane's absorption bands are not subtle, and they are not rare once temperatures fall low enough. The molecule becomes abundant and its infrared fingerprints deepen. A substellar atmosphere is a layered place. At different depths, pressure and temperature change, and the emergent light comes from different layers depending on wavelength. Where the atmosphere is transparent, we see deeper, hotter layers, and the object looks brighter. Where methane or water is opaque, we see higher, cooler layers, and the object looks dimmer. That is why the spectrum becomes jagged. It is not just absorption in a single layer, it is a shifting view into the atmosphere's vertical structure. Clouds can complicate the picture further, although the basic story remains. Condensates can form at certain temperatures, and cloud decks can mute or reshape spectral features. Even then, methane and water often leave broad depressions that survive. When those depressions fall into the wrong filter, the photometry can imitate a dropout. The camera does not know it is sampling different atmospheric depths. It only knows that one band has fewer photons. This is where the coincidence becomes almost mechanical. Imagine a methane band centered such that it drags down the average flux across one filter, while the neighboring filter lands in a clearer atmospheric window. The color between those two filters becomes extreme. Extreme color is the currency of dropout selection. It is the signal that says something is missing here. In the cosmic dawn interpretation, what is missing is ultraviolet light erased by hydrogen and stretched into infrared. In the methane interpretation, what is missing is infrared light erased by molecules and never allowed to escape. Both stories produce the same accounting result. One filter is faint, the next is bright. The resemblance is strongest when the object is faint, because faintness blurs distinctions. At high signal-to-noise, small differences in slope and curvature can separate a galaxy from a substellar object. At low signal-to-noise, those differences dissolve into error bars. This is why the red dots were so captivating. They were not merely red, they were red in the particular way that matched a high redshift template. The photometry did not just drift into the selection region, it sat there with apparent confidence. Yet confidence in a deep field is always conditional. A deep field is a triumph of calibration and patience, but it is also a place where the background is complex. The infrared sky includes faint gradients and time-variable components that must be modelled. The detectors themselves add subtle structure. Pixel-to-pixel sensitivity variations, persistence from bright sources, and correlated noise can all affect the faintest measurements. These effects are usually small, but near the threshold they can decide whether a point is detected. A non-detection, therefore, is a statement about methodology as much as it is about the sky. It depends on aperture choice, background annulus placement, and how the noise is estimated. Change those choices slightly and the limit can shift. In dropout selection, that shift matters. A marginal flux measurement can either soften a break or sharpen it. A softened break might drop the object out of the high Z box, while a sharpened break might push it deeper inside. This is why the chapter insists on humility. The pipeline is not wrong, but the pipeline is not omniscient. It is a set of decisions that translate photons into catalogues, and catalogues into stories. The bullet cluster's lensing adds a second layer of decision-making. Lensing magnifies background galaxies, but it also distorts them. It can stretch an object into an arc, or compress it into something nearly point-like depending on the local shear. In some regions, lensing can create multiple images of the same background galaxy. In principle, that is a clue. A true high redshift galaxy might appear in more than one place. In practice, those counter-images can be too faint, or they can land on bright cluster members. Lensing models attempt to predict where images should appear, but models are approximations. They depend on the assumed distribution of dark matter, the mass of cluster galaxies, and the quality of constraints. Small differences can change whether a candidate seems consistent. Meanwhile, local contaminants do not care about lensing geometry. A nearby object will not produce counter-images, and it will not align with critical curves in any meaningful way. Yet a single object can still sit in a region where lensing made observers look harder. That is the subtle bias of lensing surveys. We observe where magnification is high, because that is where the earliest galaxies might be revealed. But by observing there, we also intensify the impact of any rare interloper that happens to be in the field. The imposter does not have to be numerous, it only has to be present, and it only has to match the selection criteria. In a small, deeply observed patch of sky, one convincing object can shape the narrative. Dust adds a softer kind of confusion. Dust does not usually create a sharp cliff like hydrogen or methane, yet in noisy data a smooth slope can masquerade as a break. If the blue flux is underestimated and the red flux is overestimated, the slope can look abrupt. Dusty galaxies at moderate redshift can also carry strong emission lines. Those lines can brighten a redder filter and exaggerate the apparent jump. The combination can mimic a high redshift colour even when the true redshift is lower. That is why the chapter refuses a single villain. Methane is a powerful mimic, but it is not the only one. The deeper point is that broadband selection is an inference. An inference has failure modes. The story, however, is not one of defeat. It is one of refinement. When a method encounters a boundary, it reveals what must be added next. Widening the filter set is the most straightforward addition. With more bands, the spectrum is sampled more densely, and coincidences become harder to sustain. A methane object must match not one colour jump, but a sequence of colours. In practice, that means targeting filters that straddle known molecular bands. If methane and water are responsible, the object will show a pattern of depressions at predictable wavelengths. If the object is a high redshift galaxy, the pattern should be different. Template libraries must also evolve. Substellar atmospheres are diverse, and their spectra depend on gravity, metallicity, and cloud properties. A young, low-gravity object can look different from an old, high-gravity one at the same temperature. Metallicity matters because it changes molecular abundances. A metal-poor atmosphere may have weaker methane or different continuum shapes. A metal-rich atmosphere may deepen certain bands, shifting colours in ways that a limited library cannot capture. Priors are the quiet partner in all of this. They encode what we think is likely before seeing the data, and they can prevent the fit from chasing implausible extremes. Yet priors must be handled carefully, because the improbable is sometimes the point. The history of high redshift astronomy is full of improbable candidates that later became accepted. Early claims were often debated, and some were overturned, but the process sharpened the tools. Each controversy forced better calibration, better modelling, and better follow-up. That is the constructive role of the red dots. They're a stress test for JWST-era photometry. They show where the old intuitions must be upgraded for a telescope that can see both the first galaxies and the coldest neighbours. Morphology provides additional texture, but it is not a silver bullet. A point-like source suggests a compact object, yet early galaxies can be compact too. Lensing can compress or stretch, and the point spread function can hide faint extensions. Still, careful analysis can help. Comparing the source profile to nearby stars, examining residuals after point spread subtraction, and checking for subtle elongation can add evidence. None of these steps alone can decide the case, but together they can shift probabilities. The most decisive tests remain motion and spectroscopy. Motion is a geometric fact, and spectroscopy is a physical fingerprint. They do not rely on the same assumptions that photometric selection requires. Spectroscopy in particular is the place where the coincidence should break. A methane-dominated atmosphere has multiple absorption bands that repeat across the near-infrared. The spectrum should show a sequence of troughs, whose spacing and depth follow molecular physics. A high redshift galaxy should instead show a single dominant break with a different redside behavior. The continuum redward of the break may slope, and emission lines may appear, but the pattern should not mimic methane's repeating structure. The difference is not merely aesthetic, it is diagnostic. This is why the chapter calls the overlap a shared colour space, rather than a shared identity. The same photometric silhouette can belong to two very different objects. The job of follow-up is to restore identity to the silhouette. JWST's sensitivity makes this both easier and harder. It makes it easier because faint objects can be detected at all, and because spectroscopy can reach deeper than before. It makes it harder because it opens a new regime where rare contaminants become visible. The red dots therefore sit at a boundary between frontiers. One frontier is cosmic time, where we search for the first galaxies and the first heavy elements. The other frontier is local and cold, where we search for objects that barely glow. That local frontier is not a distraction. Cold substellar objects teach us about atmospheric chemistry under conditions unlike those on stars. They also teach us about the population of free-floating bodies in the Milky Way, which connects to formation history. So when the red dots turned out to move, the story did not collapse, it pivoted. The edge of the universe did not retreat, but our interpretation gained a new dimension. The chapter returns again to the central question, now sharpened by the coincidence. If the dots were not first galaxies, what were they, and how many more hide similarly? How many candidates in future surveys will demand the same careful disentangling? The answer will live in classification, and classification is a kind of naming. We must decide whether the culprits are stars, planets, or objects in between. The categories matter because they imply different origins and different physics. The transition is unavoidable because the mystery has changed shape. If the culprits are local, we need to name them and explain their origin. We need to understand how such cold, faint objects form and how they wander into our line of sight. Next, we follow the evidence from colours to physical identity. The search for cosmic dawn becomes a search through the Milky Way's coldest shadows. And as the camera keeps staring into darkness, the darkness answers back, sometimes from the beginning of time and sometimes from next door. Now the story pivots again because motion answers where they are, not what they are. In the bullet cluster field, two red pinpricks did something galaxies should not do. They slid, subtly but unmistakably, across a background that stayed fixed. On screen, the effect is almost unfairly simple, and that simplicity is exactly why it convinces. The distant galaxies and faint arcs of lensing remain nailed to the same pixels, as if the cosmos were printed on glass. The two dots, however, shift position between epochs, like embers drifting across a painted night sky. In that shift, distance collapses from cosmic dawn to local space. The camera can linger on the alignment process because it is the quiet heart of the reveal. Astronomers register the images by matching dozens of faraway galaxies, then subtract one epoch from another. The subtraction leaves a ghostly residue where anything moved, and the residue points straight to the imposters. If those dots are not first galaxies, then they must belong to the Milky Way. That single inference reorganizes the entire mystery, because it flips the direction of our imagination. Instead of newborn starlight stretched by expansion, we are looking for cold, nearby bodies that barely glow. The same photons that once implied an ancient origin now imply a small, cooling object in our own stellar suburb. The candidates are ultra-cool brown dwarfs, rogue planetary mass objects, or old halo interlopers with unusual chemistry. Each option is plausible because the infrared can hide identities, especially when only a few broad filters are available. The disguise forces a hard question about categories, because the boundary between star and planet is not clean. Even the language we use, star, dwarf, planet, can feel like a set of boxes drawn onto a gradient, Astronomy likes crisp definitions, yet nature prefers gradients, and those gradients are often where the most interesting physics lives. Mass, composition, and formation history all matter, but we rarely observe them directly. When objects are isolated and faint, classification becomes a probabilistic argument built from light and motion. We're not reading a label, we're reconstructing a biography from a few spectral syllables. A star is defined by sustained hydrogen fusion in its core, a long-lived balance between gravity and pressure. Above roughly 70 to 80 Jupiter masses, gravity compresses the interior until temperatures reach millions of Kelvin. In that regime, protons can overcome their electrostatic repulsion, and fusion runs steadily for billions of years. The star settles onto the main sequence, and its luminosity becomes a predictable function of mass. The exact threshold is not a single number carved into physics, and that uncertainty matters at the margins. It shifts with metallicity and helium fraction, because opacity and mean molecular weight change the core's structure. A metal-poor object radiates energy differently, and that changes how easily the core heats under compression. Still, the guiding idea remains plain. Enough mass produces a self-sustaining furnace. Below that threshold, the core never reaches stable hydrogen burning, even though gravity still squeezes it relentlessly. The object is supported partly by ordinary gas pressure, but also by electron degeneracy pressure, quantum mechanics pushing back when matter is squeezed too tightly. Degeneracy pressure is indifferent to temperature, so heating does not easily trigger a runaway fusion state. In simple terms, the interior becomes a quantum-stiff material before it becomes a hydrogen-burning engine. That is why the object becomes substellar, a body with stellar origins but a different destiny. It can shine, sometimes brightly at first, yet it cannot lock itself onto the main sequence. It is not a star that turns off, but a body that never crosses the ignition line. The difference is subtle in words and profound in physics. Brown dwarfs sit between stars and planets in mass and behaviour, and they occupy a region once filled mostly by theory. Many form like stars, from collapsing gas that fragments in molecular clouds. The process is the same gravitational choreography: turbulence, fragmentation, and accretion, just cut short before enough mass is gathered. The embryo forms, but the pantry runs out, or the environment ejects it before it can grow. In their earliest phase, brown dwarfs can look deceptively stellar, and that deception is part of why they were so hard to confirm historically. They are hot from formation, their atmospheres roiling with convection, their spectra showing atomic lines and molecular bands. Then time asserts itself, because the internal energy reservoir is finite. Without sustained fusion, the object's brightness is a fading memory of its birth. They ignite briefly, then fade, because the furnace never fully turns on, and the word ignite is literal in a limited sense. Some brown dwarfs burn deuterium, and the most massive can burn lithium, yet these are side fires rather than the main hydrogen blaze. They provide momentary pressure support and extra luminosity, but they do not establish the long equilibrium of a true star. The deuterium burning limit is a secondary marker, not a true definition, and it's best understood as a temperature checkpoint. Around 13 Jupiter masses, central temperatures can briefly reach the level needed to fuse deuterium. That fuel is scarce, so the phase is short, often ending within tens of millions of years. In cosmic terms, it is a spark, not a career. Deuterium burning matters because it is measurable in models and sometimes in interpretation, especially for young objects. It can separate massive planets from the lightest brown dwarfs in some taxonomies, yet it does not create the long-lived equilibrium that defines a star. If hydrogen burning is a steady hearth, deuterium burning is a match struck in the dark. The lithium test adds another nuance, and it carries a quiet piece of astronomical history. Objects above roughly 60 Jupiter masses can burn lithium, while lighter brown dwarfs retain it. Historically, lithium helped confirm the first brown dwarf candidates, because it offered a chemical signature of substellar interiors. It was one of the first ways to say, with evidence, that an object could be star-like yet not a star. The phrase failed star is misleading but evocative, and the emotion in it has always been part of the debate. It implies a botched attempt, as if the object tried and fell short. In reality, the physics is simply a different outcome of collapse, governed by initial conditions and accretion history. The universe did not grade the object and mark it down, it just followed the rules. A brown dwarf can be a normal product of star formation, just below the mass needed for hydrogen fusion. In crowded nurseries, fragmentation can produce a spectrum of masses, from massive stars down to substellar embryos. Some embryos keep accreting, while others are starved or ejected. The same chaotic environment that builds stars can also scatter its smallest products into the field. Formation pathways matter because they blur labels, and the blurring is not an inconvenience but a clue. Some brown dwarfs likely form like low-mass stars in turbulent clouds, collecting gas until the local supply is exhausted. Some planetary mass objects may form in disks, then get ejected, becoming free-floating worlds with star-like kinematics. The end result can look similar, even when the beginning was different. The observational problem is that origin is hard to prove, especially when the evidence has cooled for billions of years. A free-floating object does not carry a tag that says disk-born or cloud-born. Without a natal environment, we infer history from the faintest traces in spectra and motion. Even then, the inference is often a range of possibilities rather than a single answer. In practice, observers lean on mass, spectra, and context, because origin is elusive. Mass is rarely measured directly for isolated objects, since there is no orbit to weigh. Spectra and motion become the practical identity card, even when the photo is blurry. We accept ambiguity, then try to shrink it with every additional epoch and every additional band. Brown dwarfs cool continuously after formation, and that cooling is the defining arc of their lives. They begin hot from gravitational contraction, converting potential energy into heat. Then they radiate energy away for billions of years, and the interior slowly settles toward a colder, denser state. The process is slow enough to be cosmic, yet fast enough to matter over the lifetime of the galaxy. Without sustained fusion, luminosity declines steadily, and the spectrum shifts to longer wavelengths. The cooling is not uniform, because atmospheres change phase as temperatures drop. Clouds form, dissipate, and reform with different chemistry, reshaping the emergent light. What we see is not just a temperature reading, but a weather system written in molecules. Cooling is the central reason old brown dwarfs become nearly invisible, even when they are relatively nearby. Their surface temperatures can drop from thousands of Kelvin to a few hundred. At that point, most emission is deep infrared, and visible light becomes negligible. The object is still there, still massive, yet it is optically almost absent. It helps to picture the spectrum as a moving peak, sliding redward as the object ages. A warm L dwarf still emits substantial near-infrared light, sometimes even a faint red optical glow. A cold Y dwarf pushes its peak toward mid-infrared wavelengths, where Earth's atmosphere blocks much of the signal. The physics is simple, black-body intuition, but the details are complicated by molecules and clouds. This is why JWST is relevant even when the objects are nearby, and why the discovery feels like a twist. JWST was built to catch stretched light from early galaxies, where ultraviolet becomes infrared. It also catches the cold glow of substellar bodies, whose peak emission sits in the same infrared bands. A telescope optimized for the first light also becomes a detector for the faintest local heat. In the visuals, the irony is striking, and it plays well in silence. The telescope designed to look back toward the first starlight also becomes a lantern for local darkness. The same filters that isolate cosmic dawn can accidentally spotlight the Milky Way's coldest drifters. In a single field, the oldest galaxies and the coldest neighbours can compete for the same pixels. Spectral classes track this cooling sequence in the field, and they are more than labels on a chart. L dwarfs are warmer and often show dusty clouds and metal hydrides. Their atmospheres can contain silicate and iron condensates, which scatter and absorb light, reddening their colours. In images, that redness can look like distance, even when it is simply dust and temperature. As temperatures fall, those clouds sink or break apart, and the atmosphere becomes clearer in some bands. The spectrum changes abruptly, and the object transitions into the T-class. T-dwarfs are cooler and show strong methane absorption that reshapes near-infrared colours. The transition can be dramatic because the same temperature drop can reorganize the dominant molecules. Methane is not just a label, it is chemistry in action, and it is a signpost of cooler equilibrium. At lower temperatures, carbon prefers to reside in methane rather than carbon monoxide. That shift rearranges the molecular opacity, carving deep absorption bands that dominate the near-infrared. In plain terms, methane steals photons in specific places, and the filters notice, Dwarfs push the sequence to the coldest known temperatures, and they begin to resemble gas giants more than stars. Their atmospheres can approach giant planet conditions, with ammonia features and extreme molecular absorption. They can be only a few hundred Kelvin, sometimes comparable to Jupiter. At that point, the word dwarf feels almost too warm. At those temperatures, the atmosphere becomes a laboratory of exotic weather, and the visuals can suggest it without showing it directly. Water can condense into clouds, and sulfides and chlorides can form hazes. The spectrum is then shaped by both composition and pressure, like a fingerprint pressed into infrared light. Even small changes in gravity can change the pressure scale height, and that changes how deep we see. Methane is the key imposter molecule for dropout searches, and the mechanism is almost mischievous. In T-dwarfs, methane bands carve out deep troughs in near-infrared filters. Those troughs can mimic a sharp photometric break, the same silhouette used to flag high redshift galaxies. The algorithm sees a cliff and assumes cosmology, even when the cliff is atmospheric. A dropout search is a clever trick with a vulnerability, and that vulnerability grows at the faintest limits. You look for an object that is bright in redder filters, but nearly absent in bluer ones. For galaxies at extreme redshift, the missing light comes from intergalactic hydrogen, absorbing ultraviolet photons. The technique is powerful because the physics of hydrogen absorption is universal, but it is not unique. In a brown dwarf, the missing light comes from its own atmosphere, and that difference is invisible to broadband photometry. Molecules absorb in wide bands, leaving only narrow windows where photons escape. When broad filters average over those windows and troughs, the result can look like a cliff. The cliff is real in the data, but its cause is not what the search expects. Water vapor and collision-induced absorption add to the sculpting, and they do it in a way that can erase context. Water bands suppress broad regions, and dense hydrogen can darken the continuum through pressure effects. Collision-induced absorption is subtle in name, yet powerful in outcome, because it erases light without discrete lines. It is the atmosphere's way of dimming the lamp without leaving a sharp signature. The combined spectrum becomes a set of narrow windows where light escapes, like small skylights in a roof of absorption. In one filter, the object can appear bright, and in the next it can nearly vanish. That is the same pattern a high redshift selection algorithm is trained to celebrate. The algorithm is not wrong to be excited, it is simply under-informed about imposters. A high redshift galaxy has a different physical cause for missing light, and that cause is written into the structure of the universe. Intergalactic hydrogen removes rest frame ultraviolet, and cosmic expansion shifts that cutoff into the near-infrared. The break is not molecular, it is cosmological, and it marches redward with redshift. In principle, that march is a clean ruler, but in practice the ruler is blurred by noise. Yet broad bands do not explain causes, they summarize outcomes, and that is where the confusion lives. In broad bands, both scenarios can look like a cliff. The data point is the same, while the universe that produced it could not be more different. The telescope records photons, and interpretation supplies the story. So the mystery reframes itself as local archaeology rather than cosmological history. The same dataset that promised the first galaxies now samples the Milky Way's faintest inventory. The edge of cosmic time overlaps the outskirts of our own neighbourhood in infrared colour space. It is an overlap created by physics, not by mistake. The bullet cluster field is a particularly dramatic stage for this overlap because it was chosen for its ability to magnify the distant universe. It is famous for gravitational lensing and for the separation of mass and hot gas inferred from X-ray maps. In a field built to study distant structure, the foreground can still whisper. The whisper becomes audible only when the exposure is deep enough. Why are these objects so hard to find in ordinary surveys? They are intrinsically faint, especially in optical bands where most sky catalogues are built. Even nearby, an old brown dwarf can be below detection limits in visible light, effectively absent from traditional star maps. It is not missing from the sky, it is missing from the wavelengths we historically preferred. The reason is not simply that they are small, although size does matter for total luminosity. Their temperatures are low, so their blackbody-like emissions shifts away from optical wavelengths. A cool atmosphere also contains strong molecular absorbers, which further suppress the little optical light that might escape. The object becomes doubly hidden, cold enough to emit elsewhere, and molecular enough to absorb what remains. Their emission peaks in infrared, But infrared surveys have historically been shallower, and that history shapes what we think the neighbourhood contains. Space missions like 2MASS and WISE revolutionised the census, yet they were designed for all sky coverage rather than extreme depth. That trade-off leaves the faintest, coldest objects behind. The sky is full, but our earlier maps were drawn with thicker lines. Ground-based infrared programs have found many, but they face the bright thermal background of Earth's atmosphere, which is a constant adversary. The sky itself glows in infrared, and water vapour adds variability. Detecting a few hundred Kelvin object at tens of parsecs becomes an exercise in patience and statistics. You stack exposures, calibrate carefully, and hope the signal survives the atmosphere's shimmer. The oldest population is the hardest, because it has had the most time to cool, and cooling is merciless at late times. Cooling curves steepen as luminosity drops, so a small temperature change can mean a large luminosity drop. The objects become not just dim, but selectively dim in the bands we most often use. They slip into the gaps between survey sensitivities. Distance adds another layer of invisibility, and it works even when the object is technically nearby. A cold object at tens of parsecs can be faint enough to blend into noise in typical exposures. In deep extragalactic fields, the exposure time is extreme, so the same object becomes detectable. The paradox is that we find local neighbours by staring past them for a very long time. That creates a trapdoor in survey design, and it opens precisely because JWST is so sensitive. Deep fields are chosen to avoid bright stars and minimise foreground clutter. The selection works for ordinary stars, yet JWST's sensitivity is so high that even in those carefully selected windows, faint local substellar objects can still appear. The trapdoor is not in the sky, it is in our assumptions about what counts as foreground. In the visuals, the trapdoor feels like a reveal, because the field looks empty of foreground stars at first glance. The image seems surgically clean, a dark stage set for distant galaxies. Then a deeper integration pulls up a point source that was always there, hidden below the threshold of earlier surveys. The point source is not a defect, it is a resident. Contaminants become discoveries when the instrument reaches new depth, and the shift in attitude is part of the story. The pipeline flags a dropout because the colours match the high Z selection box. Then time reveals motion, and the dropout becomes a nearby wanderer. The same object changes category without changing itself. This is not a trivial bookkeeping error, and it matters because the rarest claims are the most fragile. It changes how confident we can be in the rarest high redshift candidates because the sample sizes are tiny. When you expect only a handful of true cosmic dawn galaxies, even one imposter can distort the story. A single contaminant can pull a luminosity function, or inflate a headline simply because the statistics are thin. It also reveals a hidden population that is otherwise difficult to census, and that population is scientifically valuable on its own. Every misidentified galaxy that turns out to be a brown dwarf is still a valuable data point. It is a local fossil uncovered by a telescope aimed at the early universe. The mistake becomes a measurement of the Milky Way's faint inventory. To interpret the moving dots, kinematics becomes a clue, and kinematics is a kind of galactic genealogy. Disk objects share the Milky Way's rotation, with modest velocity dispersion. Halo objects move differently, often faster and on more eccentric orbits, reflecting an older population assembled through mergers. Motion is not just speed, it is membership. The distinction is statistical, not absolute, and the chapter's mystery lives in that uncertainty. A disk object can have an unusual velocity, and a halo object can pass through the disk. Still, population kinematics gives us a framework, an interpretive map for motion. The map is not perfect, but it narrows the range of plausible histories. Proper motion is the first telltale sign of proximity, and it is one of astronomy's oldest distance clues. Nearby objects sweep larger angles for the same transverse speed because the baseline is shorter. In a one-year baseline, measurable motion implies a distance far smaller than any galaxy, regardless of brightness. The dot can be faint, but it cannot be far if it moves. Astrometry is unforgiving in that way, and it is a rare kind of certainty in a field full of inference. A galaxy at billions of light years is effectively fixed, because its angular motion is vanishingly small. A brown dwarf at tens of parsecs can shift by fractions of an arcsecond, enough for JWST to notice. The background becomes a ruler, and the dot betrays itself against it. The direction and magnitude of motion can hint at population membership, and the hint becomes stronger when combined with colour. A high proper motion can indicate either closeness or high velocity. Combined with red colours and faintness, it can suggest an old, cold object with thick disk or halo kinematics. The motion becomes a narrative arrow pointing toward age. Parallax can, in principle, sharpen the distance estimate, and it is the clean geometric complement to proper motion. As Earth orbits the Sun, nearby objects trace a tiny ellipse against the background. With enough epochs, the parallax signature separates distance from true space motion, turning a drifting dot into a mapped neighbour. The ellipse is small, but it is honest. Age matters because it controls temperature and luminosity, and brown dwarfs never stop evolving in that sense. A brown dwarf does not settle into a stable brightness like a main sequence star. Older usually means colder and dimmer, so the faintest objects can be the oldest survivors. When you see an exceptionally faint substellar object, you're often seeing time made visible. That idea carries a quiet historical weight, because it connects local darkness to deep time. The Sun is about 4.6 billion years old, and the Milky Way's disk is older still. If these objects are ancient, they have been cooling since before complex life appeared on Earth, radiating their heat into interstellar night. They are not relics of the early universe, but they are relics of the galaxy's early epochs. Metallicity and gravity also matter, because they reshape spectra in ways that can mimic distance or temperature. Old populations tend to be metal-poor and high gravity, which can alter methane and water band depths. A metal-poor atmosphere changes the balance of molecules and reduces certain opacities, shifting colours into unexpected corners. The same filter set can therefore misread an old object as an exotic one. High gravity compresses the atmosphere, increasing pressure, broadening and collision-induced absorption. The same temperature can produce different colours depending on gravity, which is effectively a proxy for mass and age. That is why photometric classification can be treacherous at the extremes. The spectrum is not only a thermometer, it is also a barometer. So what makes these two special is the combination of traits, and the combination is hard to fake. Extreme faintness suggests low luminosity and advanced cooling, not merely a modest distance. Very red colours suggest strong molecular sculpting, and a spectrum peaking beyond the optical. Measurable motion anchors them as nearby. Motion plus red colours points to ultracool substellar bodies rather than distant galaxies, and the logic is almost geometric. The simplest explanation is late T or Y dwarfs, possibly with unusual metallicity or gravity. Their faintness also hints they could be very old. If they are older than the Sun, they have had billions of years to cool. That would make them local fossils drifting quietly through the disk, while remaining nearly invisible to most surveys. It also raises a thought-provoking question about our own neighbourhood. How many such bodies pass within a few dozen parsecs, uncounted, because no one stared long enough in the right infrared bands? The galaxy could be threaded with cold wanderers that only the deepest cosmology programs can see. In the visuals, imagine a cold ember crossing a cathedral of distant light, and let the scale contrast do the work. Behind it, the bullet cluster's lensed galaxies arc like thin brush strokes, stretched and brightened by gravity. In front, the substellar object glides, silent, indifferent, and close enough to betray itself. The foreground dot is small, yet it steals the scene by moving. Rogue worlds remain a competing possibility, and the possibility stays alive because the data are sparse. A free-floating planetary mass object can be similarly cold and faint, especially if it formed long ago. Without a host star, it would still cool, and its spectrum could resemble the coldest brown dwarfs. The infrared does not easily reveal whether the object ever had a sun. The difference between a rogue planet and a low-mass brown dwarf is partly philosophical, yet also physical. Did it form in a disk and get thrown out, or did it collapse directly from a cloud fragment? The light alone may not tell us, because both end states can converge in temperature. At a few hundred Kelvin, the atmosphere becomes a common destination for different origins. Distinguishing brown dwarf from rogue planet is difficult without mass, and mass is the hidden variable in almost every substellar story. Mass requires a dynamical measurement, a companion, or a model-dependent inference from luminosity and age. For isolated objects, classification often remains probabilistic, expressed as ranges rather than certainties. We can say what is likely, but we must also say what is not ruled out. Even the models carry uncertainties, and the uncertainties are not academic when the objects are this cold. Atmospheric chemistry at a few hundred, Kelvin depends on cloud physics, vertical mixing, and incomplete molecular line lists. When we fit spectra, we're also testing our understanding of cold atmospheres, not just labeling the source. Every fit is a negotiation between data and theory, yet the broader implication is clear, and it is bigger than two dots in one field. The Milky Way contains a large faint reservoir of substellar bodies, from warm L dwarfs to the coldest white dwarfs. Deep JWST fields, built for cosmology, can accidentally sample that reservoir at its coldest edge. The telescope becomes a census tool for objects that were never the headline. That reservoir matters for more than bookkeeping, because it speaks to how stars form in the first place. It informs the low-mass end of star formation, and it constrains how efficiently clouds fragment. It also hints at how many free-floating planetary mass objects might drift between stars, unseen except in the deepest infrared. The galaxy's mass budget and its formation history both depend on what we count. This forces a methodological upgrade for cosmic dawn searches, and it is an upgrade driven by success rather than failure. Photometric redshifts can be seduced by template incompleteness, especially for extreme T and Y dwarfs. Selection at the limit can amplify rare imposters into headline candidates because the statistical prior is fragile. When the expected number of true high-Z galaxies is small, the cost of one mimic becomes large. The history of brown dwarf discovery offers a cautionary parallel, and it is worth remembering how long the gap persisted. For decades, they were predicted but elusive, hiding between categories and below sensitivity thresholds. When infrared surveys improved, the sky did not change, but our census did, and the definition debates followed. The objects were always there, waiting for the right wavelengths and the right patience. Better tests must be built into the workflow, and the tests should be designed to fail fast when an imposter is present. Multi-epoch imaging adds motion constraints early, because true high-Z galaxies should be stationary. Even a short baseline can flag a nearby object, especially when the background provides a stable reference grid. Time becomes a filter, just as powerful as any wavelength. Expanded filter coverage can catch multiple molecular troughs that a single dropout pattern hides, and the pattern recognition becomes more robust. Methane and water absorption produce a repeating structure across bands, while a Lyman break is a single sharp cutoff. More colours do not guarantee truth, but they reduce ambiguity. They allow the data to ask repeatedly whether the cliff is atmospheric or cosmological. Spectroscopy remains the decisive fingerprint, and it is where the two stories diverge unmistakably. A methane-dominated atmosphere shows repeated absorption bands across the near-infrared, with characteristic shapes set by temperature and gravity. A true Lyman break galaxy shows a break tied to redshift, plus nebular lines and a different continuum behaviour. One spectrum is carved by molecules, the other by hydrogen absorption and galaxy physics. Spectroscopy also changes the emotional texture of the search, because it replaces silhouettes with structure. Photometry gives hints, like shadows in fog. A spectrum is a voice, revealing whether the object speaks in molecular absorption or in the redshifted language of galaxies. The same faint dot becomes either a nearby weather system or a distant stellar nursery. The stakes rise because future surveys will go deeper and wider, and the overlap region will only grow. The deeper we push, the more the overlap region fills with rare locals and rare galaxies. Without careful tests, the boundary between them becomes a recurring source of confusion. The confusion is not an embarrassment, it is a predictable consequence of exploring new parameter space. That boundary is not a failure of instruments, but a consequence of success, and it is one of the chapter's central observations. When sensitivity improves, the universe offers more objects per pixel and more ways to be fooled. The solution is not to retreat, but to sharpen the logic of identification. Better logic is the price of better data. The bullet cluster field becomes a mirror for the entire enterprise. We thought we were mapping the first galaxies, yet we also mapped the coldest nearby light. The universe did not trick us to embarrass us. It tricked us to refine us. At this moment, the edge of the universe moves again, not in distance but in method, and that movement is the real pivot. The overlap between cosmic dawn and local cold wanderers becomes a design constraint. Every future claim must prove it is not sliding across the sky. In the deepest images, motion is not a detail, it is a verdict. The chapter closes by tightening the central question and letting it hang with its full weight. If those two faint red dots were not galaxies from the first 200 million years, what were they? What does their disguise reveal about how we search for the dawn of cosmic time? The question is not only about two objects, but about the rules we trust. There is a deeper observation hiding inside that question, and it reaches beyond this field. Our most ambitious surveys are not just maps of space, they are tests of interpretation. When a brown dwarf can masquerade as the earliest galaxy, the lesson is about humility and rigour, not embarrassment. The universe is not obligated to be easy to classify. The transition is unavoidable, because the mystery has changed shape, and our tools must change with it. We now hunt not only for distance, but for identity, using spectra, motion, and population context. Next, we ask what else in the deepest images might be misidentified, and how to build better tests for the true first galaxies. The two red pinpricks did not just move across the bullet cluster field, they moved the burden of proof, because deep fields are now crowded with lookalikes, and the faint sky no longer belongs to galaxies alone. In the image, the scene is almost too clean, almost too composed. A velvet black background holds a scatter of pale galaxies, some stretched into thin arcs by gravity, and others smeared into faint commas by shear. Near the centre sit two tiny points of red light, sharp as needle pricks, as if they were stamped onto the detector. Then the comparison frame arrives, and the stillness breaks. The dots have slid, not by pixels that shout, but by a shift that whispers, a nearby object, close enough to drift. The visual difference is subtle, yet the implication is loud. In a deep field, we expect the distant universe to be fixed, because cosmological sources do not crawl across the sky on human timescales. When something moves against a background of stationary galaxies, it is not merely an oddity, it is a geometric confession that the object belongs to the local neighbourhood. We return to the central fear behind the central question. If nearby objects can masquerade as cosmic dawn, then every record-breaking claim becomes a suspect until proven otherwise, and the suspicion is not cynicism. It is the price of working at the limit, where the data are thin and the consequences are loud. That limit has a history and it is worth remembering. In the Hubble era, a handful of ultra-faint dropouts could dominate the conversation, because the sky was expensive to observe and the infrared was shallow. A single candidate at the edge of detectability could tilt a narrative about the first billion years. JWST did not remove that temptation, it amplified it, because it made the frontier populous. JWST changed the game by making the faint sky routine. With its segmented mirror and cold, stable optics, it turns what used to be heroic detections into catalogue entries, and that power reshapes the statistics of discovery. The observatory's thermal design matters here, because a colder telescope emits less infrared glow, and less glow means a darker background. In that darker background, the same exposure time reaches deeper, and the deep becomes normal. When surveys go deep enough, the rare becomes common in the selected sample, even if it is rare on the sky. That statement sounds paradoxical until you remember how selection works. A survey does not harvest the universe uniformly, like a net dragged through water. It harvests through a set of filters, thresholds, and human choices, and those choices preferentially keep the weird. That is a subtle but ruthless point. Selection does not sample the universe evenly. It samples the universe through a set of filters, thresholds, and human choices, and the objects that survive are often the ones sitting in the distribution's tails. Those tails are where cosmic dawn should live, but they are also where imposters hide. In practice, the tails are built from colours, and colours are built from broad filters. Each filter is a wide bucket of wavelengths, and a measured magnitude is an average over whatever structure sits inside that bucket. If the structure is complicated, the average can be misleading. At high signal-to-noise, you can see the complexity. At the limit, you see only the bucket totals, and the buckets can lie. Contamination is not a footnote to the dropout method. It is a predictable outcome of pushing extreme colour selection into new depth and new wavelength space, especially when the selection is designed to find objects that are almost invisible. The deeper the imaging, the more the method becomes sensitive to odd spectra, rare stars, and statistical flukes. The dropout logic still begins with a real physical anchor. A high redshift galaxy should show a sharp break where neutral hydrogen removes rest frame ultraviolet light, and that break is not an aesthetic feature. It is a consequence of atomic physics, because hydrogen absorbs photons that can ionize it, and the early universe contained a great deal of neutral hydrogen. In practice, the break is tied to the Lyman series. Photons bluer than Lyman alpha are scattered and absorbed by intervening hydrogen clouds, and photons bluer than the Lyman limit are even more strongly suppressed. The absorption is not a single wall, but a forest of lines that thickens with distance. As the universe expands, those rest frame ultraviolet wavelengths slide into the near-infrared, and JWST is built to see them. The mapping is simple in principle and unforgiving in practice. If a rest frame feature at 1216 angstroms is observed at 2 microns, the implied redshift is enormous, because the wavelength has been stretched by a factor of roughly 16. That stretch is not a guess, it is the definition of cosmological redshift. Yet the measurement is only as good as the identification of the feature. But the sky contains other sharp breaks that have nothing to do with expansion. Ultracool atmospheres and dusty sources can carve cliffs inside broad filters, and they do it with molecular chemistry rather than cosmology. The same selection box that catches a galaxy at Z greater than 10 can also catch a cold object a few dozen parsecs away. The lesson broadens beyond 2 dots. The universe's earliest galaxies are not the only faint red things in the sky, and JWST is sensitive to all of them, whether we invited them into the experiment or not. In deep fields, every photon counts, and every photon has to be interrogated. In the Milky Way, the most dangerous imposters are rare populations with extreme infrared colours. Late T dwarfs, Y dwarfs, and planetary mass objects can land inside high Z selection boxes because their emergent light is sculpted into peaks and valleys. Their temperatures can be only a few hundred Kelvin, closer to a warm oven than to a star. At those temperatures, the physics shifts regimes. The atmospheres are cool enough for molecules to dominate opacity, and in some cases for condensates to form clouds that redistribute flux. The objects are supported by electron degeneracy pressure rather than sustained fusion, which is why they cool steadily over time. A young brown dwarf can be comparatively bright, while an old one can fade into near invisibility. Historically, these objects were almost theoretical. Brown dwarfs were proposed as failed stars long before they were found, partly to explain missing mass, and partly to fill a logical gap in star formation. The first confirmed examples in the 1990s arrived as a surprise that quickly became a new census problem. As infrared surveys improved, the spectral sequence extended from L to T and then to Y, each step colder and fainter. The naming hides a deeper point about classification. These letters are not merely labels, they encode changing chemistry, changing pressure, and changing spectral morphology. In L dwarfs, metal hydrides and dust clouds shape the near-infrared. In T dwarfs, methane becomes a defining absorber. In Y dwarfs, ammonia and even more extreme conditions begin to appear, and the flux retreats into narrow windows. Their spectra are not smooth. Methane and water create deep absorption troughs, and collision-induced absorption from H2 can suppress the continuum in wide bands, especially when pressure is high in the atmosphere. The result is a spectrum that looks like a mountain range seen through fog, bright windows separated by dark molecular gulfs. Those windows fall in familiar near-infrared bands. The J band can rise into a peak because opacity is lower there, while H and K can be chewed away by methane and water. In a high-resolution spectrum, the troughs have edges and shoulders. In broadband photometry, they collapse into a few numbers, and the numbers can masquerade as cosmology. In broadband photometry, those troughs can mimic a single step. A filter averages over structure, and the average can look like a Lyman break, particularly when the object is detected in only a handful of bands. The dropout method is built on missing flux, and cold atmospheres are experts at hiding flux. Noise makes the disguise easier. Near the detection limit, a non-detection is not a hard zero, it is a probability distribution clipped by thresholds. A faint positive fluctuation in the redder band, paired with a negative fluctuation in the bluer band, can manufacture an extreme colour. The selection box does not know whether the colour is astrophysics or statistics. Dust adds a different kind of mimicry. A reddened star or a dusty galaxy can tilt the continuum, and noise can sharpen that tilt into an apparent cliff, especially near detection limits where uncertainties are asymmetric. Dust grains do not care about redshift, they care about wavelength, and they preferentially dim the blue. In a visualization, dust is easy to picture. Imagine a white beam passing through smoke, the blue fading first, the red lingering longer, and the spectrum leaning as if gravity has pulled it down. In a catalogue, that same leaning becomes a colour, and the colour becomes a candidate. Dust also carries history because it is forged in stars and distributed by winds and explosions. In the early universe, dust content is a question mark, and in the Milky Way, it is a known nuisance. That asymmetry matters when you interpret a red slope. Is it the first generation of galaxies, already enriched, or is it a nearby object viewed through a dusty corridor? Transients add another trap. A supernova, a variable star, or an artifact of time-variable backgrounds can appear in one epoch and vanish in another, and the vanishing can be mistaken for a dropout signature. Even the sky itself is not perfectly steady, because zodiacal light changes with pointing and season. Zodiacal light is sunlight scattered by interplanetary dust, and it sets a floor under deep infrared imaging. JWST's orbit at L2 keeps Earth's thermal glow out of the way, but it cannot remove the solar system. Subtle background changes can push marginal sources above or below detection, and the catalogue can interpret that as astrophysics. In ultra-deep imaging, even a small transient rate matters. The selection is so aggressive that a few oddities can dominate the most extreme candidates, and the most extreme candidates are the ones that get the headlines. When the expected number of true Z greater than 12 galaxies is small, the denominator is fragile. This is why the imposter problem grows with depth. The deeper the field, the more the sample is defined by the tails of distributions, and the tails are where measurement errors and astrophysical rarity overlap. A faint source with a noisy colour can jump categories with a single sigma's worth of fluctuation. The tails are where astronomy likes to find revolutions. The tails are also where classification breaks first, because priors are weakest and templates are incomplete, and because our intuition is trained on brighter, nearer populations. At the limit, we're often extrapolating beyond the training set. There is also a human factor that is easy to ignore. When a candidate sits near the edge of a plot, isolated and extreme, it feels like a discovery. The mind is drawn to outliers because outliers promise a story. Yet the universe produces outliers in many ways, and not all of them are cosmic. The method still works in aggregate, and that is not a contradiction. Large samples average down contamination, and the luminosity function emerges from statistics, because the imposters are not perfectly correlated with the galaxies. When you count hundreds, a few mistakes do not control the shape. In other words, population studies can be robust even when individual objects are ambiguous. If contamination is roughly understood, you can marginalize over it, and the uncertainties can be carried forward honestly. The trouble begins when a single object is treated as a cornerstone. Cornerstones demand stronger proof than averages, but individual record breakers are the most vulnerable. When the expected number of true Z greater than 10 galaxies is small, one imposter can rewrite a headline, and the headline can reshape theory. A single bright candidate can imply that galaxies formed earlier, faster, and more efficiently than models predicted. That implication is not cosmetic, it is structural. Early brightness can be interpreted as unusually massive halos, unusually efficient star formation, or unusually top-heavy stellar populations. It can even pressure assumptions about feedback, dust, and the escape of ionizing photons. One dot can tug on many threads. The bullet cluster field makes this vulnerability sharper. Lensing magnification encourages us to chase the rarest objects, and it also changes what looks compelling, because it lifts faint sources above the detection threshold. The field itself is a gravitational machine, bending background light into arcs that look like brushstrokes. In the visuals, those arcs are more than decoration. They are the signatures of a mass distribution dominated by dark matter, mapped through the distortion of background galaxies. The bullet cluster earned its fame because it separated mass from light, showing that most mass is not in hot gas. In that same field, we now face a different separation, between distant galaxies and nearby imposters. Magnification does not create proper motion, but it can bias attention. It can elevate a foreground interloper into the follow-up queue, simply by making it detectable, and by placing it near dramatic lensing features that signal high redshift to the human eye. In a crowded, beautiful field, aesthetics can quietly influence triage. There is an additional subtlety in lensing fields. The magnification varies across the image, and the effective survey volume becomes complicated. That complexity can inflate the apparent importance of a single candidate, because the inferred intrinsic luminosity depends on the lens model. If the object is not even lensed, because it is local, then the entire calculation is misapplied. So the mystery reframes itself from discovery to discipline. The question becomes how to build truth tests that survive JWST-era sensitivity, where the instrument can deliver exquisite images faster than we can deliver certainty. The era of one deep image, one bold claim is ending. The first guardrail is to admit how selection really works. Color cuts are not truth, they are triage, and triage must be followed by confirmation, because it is designed to be permissive. A permissive net catches more fish, but it also catches seaweed. Photometric redshifts are powerful but conditional. They choose the best explanation among the templates provided, not among all physical possibilities, and that distinction matters at the frontier. A code can be perfectly optimized and still be wrong, if the correct answer is absent from its menu. This is not a flaw in computation, it is a limitation of representation. The algorithm can only compare hypotheses it has been given, and its confidence can be an artifact of missing alternatives. A narrow template set can produce a narrow answer with a wide smile. The output looks definitive, but it is conditional on the library. Template incompleteness is an invisible instrument systematic. If the library undersamples ultra-cool dwarves, the code can prefer extreme redshift by default, because the Galaxy templates are the only way to explain a missing band. The output looks quantitative, but the premises are qualitative. The fix begins with better priors. We must encode that Z greater than 15 galaxies are rare, while certain Milky Way contaminants are plausible at faint limits, and that plausibility depends on galactic latitude and depth. Priors are not prejudice, they are a statement of what the sky usually contains. Priors also have to respect survey geometry. A field near the galactic plane should be swimming in stars, while a high latitude field should be cleaner, though never empty. Even at high latitude, the thick disk and halo contribute rare, fast-moving objects. If you ignore that structure, you misread probability as surprise. But priors cannot become a veto on surprise. The goal is to prevent easy mistakes without forbidding the unprecedented, because cosmic dawn is supposed to be surprising, and because nature does not consult our expectations. The art is to make the prior strong enough to resist noise, yet weak enough to allow discovery. The next guardrail is to expand the contaminant menu. Brown dwarf templates must span gravity, metallicity, clouds, and non-equilibrium chemistry, because these atmospheres are not simple black bodies. Vertical mixing can dredge up molecules that should not be abundant at equilibrium, changing colors in ways that mimic redshift. Those parameters move absorption depths and windows. A low-gravity object can mimic a different temperature, and a metal-poor halo dwarf can shift colors into exotic corners because fewer metals change opacity and pressure structure. Even clouds, patchy condensates, can brighten one band while dimming another. The point is not that models must be perfect. The point is that models must be broad enough to include the plausible. If a template library covers only the median brown dwarf, it will miss the weird ones, and the weird ones are exactly what deep fields surface. JWST is a machine for finding the tails, so the templates must follow. Modelling must also include the galaxy itself. Galactic structure models predict how many cool dwarfs should appear in a field, given latitude and depth, by combining stellar density profiles with luminosity functions and kinematics. The Milky Way is not uniform. It has a thin disk, a thick disk, and a halo. Each component has a different scale height and a different velocity dispersion. The thin disk is dense and relatively cold in velocity space, while the thick disk is sparser and kinematically hotter. The halo is sparser still, but it can contribute metal-poor objects with unusual colors and large proper motions. A deep field samples all three, whether we acknowledge it or not. That prediction becomes a quantitative expectation. If the observed number of extreme red point sources exceeds the model, either the model is wrong or the selection is leaking, and both possibilities teach something. A leak warns of contamination, while a mismatch can reveal missing populations in our galaxy. This is how contamination becomes measurable instead of anecdotal. You compare candidate counts to a forward model of the Milky Way and the survey selection function, then you ask whether the numbers reconcile without invoking impossible early galaxies. The comparison turns anxiety into a testable hypothesis. Still, models do not settle individual identities. The decisive step is to add orthogonal evidence that does not rely on the same photometric coincidences, because coincidences are what imposters exploit. Orthogonal evidence means a different observable, with different systematics. Spectroscopy is the clearest orthogonal test. It resolves the degeneracy by measuring where the light is missing, not just whether a filter is faint, and it does so across continuous wavelength. Instead of one number per band, you get a curve with structure. A real high redshift spectrum should show a break at a specific observed wavelength. The break location sets redshift directly, because the rest frame Lyman features are known, and the mapping is simple multiplication by 1 plus z. In a spectrum, the cliff has an address. That address can be checked against the photometry. If the photometric dropout suggested a break between two filters, the spectrum should place it there, not somewhere else. If the spectrum shows a different shape, the photometric story collapses. Spectroscopy does not merely confirm, it adjudicates. Redward of that break, the continuum should behave like starlight filtered by dust and age. It can slope, but it should not show repeating molecular troughs, and it should not oscillate with the periodicity of methane bands. Galaxies are messy, but their mess is different. A high Z spectrum may also show emission lines. Lines like H-beta, O3, or even Lyman alpha in rare cases can appear, and their wavelengths must be consistent, because a single line can mislead if misidentified. A robust redshift is a pattern, not a guess. Those lines are not guaranteed at the highest redshifts, but when they appear they are decisive. A coherent line set locks the redshift and exposes low Z imposters, because the line ratios and separations carry the physics of ionized gas. Even a modest signal can settle an argument. A cool dwarf spectrum should instead show molecular absorption patterns. Methane and water bands repeat across the near-infrared, creating multiple valleys and peaks that align with laboratory and atmospheric models. The spectrum looks carved, as if someone took a chisel to the continuum. The pattern is a fingerprint, not a single cliff. Even at low resolution, the spacing of troughs is hard to fake with a galaxy continuum, and the overall shape often includes a distinctive J-band peak that stands out. If you know what to look for, the imposter announces itself. There is a quiet elegance to that announcement. The same molecules that make a brown dwarf cold and dim also make it identifiable. Chemistry becomes a tag, and the tag survives distance ambiguity. In a sense, the contaminant carries its own label, if we have the patience to read it. This is where JWST's instrument suite becomes the story's turning key. NearSpec and NIRISS can turn photometric hints into spectroscopic proof, and they can do it at flux levels that once belonged only to imagination. The telescope is not just a camera, it is a laboratory in orbit. NearSpec provides multi-object and integral field spectroscopy. It can measure breaks and lines for many candidates, and it can do so at faint flux levels because its detectors are sensitive and its background is low. In multi-object mode, dozens of targets can be tested in one exposure. In a lensing field, that multiplexing matters. Candidates are scattered among arcs and cluster members, and the field is crowded with distractions. But NearSpec can still place shutters on selected points. The instrument turns a chaotic scene into a controlled experiment. NIRISS offers slitless spectroscopy and wide field coverage. It can catch spectral shapes for objects that are hard to place behind a slit, especially in crowded lensing fields, and it can reveal whether a spectrum is smooth or molecularly sculpted. Slitless data can be messy, but it is democratic. Strategy matters as much as hardware. Observers choose resolutions and wavelength ranges to target the suspected break, then check for molecular structure across the band, because a true Lyman break should not repeat. The observation plan is a hypothesis written in exposure time. Even the choice of wavelength coverage is a form of skepticism. If the candidate is claimed at extreme redshift, the break should fall in a predictable region, and the spectrum should be designed to straddle it. If the candidate is a cool dwarf, the spectrum should reveal multiple absorption complexes. The same exposure can be a fork in the road. A confirmation pipeline is therefore not optional. It is a stage process that begins with photometry, then demands spectra, then demands time-domain validation, and each stage is designed to fail fast on imposters. The pipeline is a discipline, not bureaucracy. Time-domain validation is the other orthogonal test, and it is newly practical. Multi-epoch imaging can screen for proper motion and parallax even in ultra-deep fields, because JWST's pointing stability and repeatability enable precise alignment. The sky becomes a measuring grid. The logic is brutally simple. A galaxy at Z greater than 10 will not measurably shift in a year, while a nearby dwarf can drift by tens of milliseconds, depending on distance and velocity. Motion is a local signature, and the early universe cannot imitate it. JWST's stable PSF and precise astrometry make this test stronger than before. The background galaxies form a reference grid, and the candidate is measured against it, frame to frame, with careful distortion correction. The measurement is delicate, but the conclusion can be blunt. Proper motion is not just a yes or no. Its magnitude and direction constrain distance and kinematics, and they hint at disk, thick disk, or halo membership. Because different galactic components have different velocity distributions, a moving point can be placed into the Milky Way's architecture. Parallax adds geometry if enough epochs are taken. A parallax wobble separates true transverse velocity from distance, turning a moving dot into a mapped neighbour, and it can even suggest whether the object is unusually nearby for its faintness. Geometry is the oldest truth test in astronomy. There is a poetic continuity in that. We used parallax to measure the distances to nearby stars centuries after it was proposed, and we used it to build the first reliable cosmic distance ladder. Now the same geometry returns as a guardrail against cosmological overreach. The oldest method becomes a modern filter. This is why multi-epoch imaging should become routine validation. It is a cheap discriminator compared to spectroscopy time, and it fails fast on foreground interlopers, saving precious hours on the most oversubscribed instruments. In a world of limited telescope time, efficiency becomes ethics. It also catches transients that masquerade as dropouts. If a source appears in one epoch and fades in another, it is not a stable high Z galaxy, and the light curve itself becomes a clue to its nature. A supernova does not need to be understood to be excluded. The community is already shifting toward these standards. JWST deep fields now plan repeat visits, not only for depth, but for motion screening, and teams design programs with confirmation in mind from the start. The cadence of observation becomes part of the argument. This change has a cost. It demands patience, careful astrometric calibration, and a willingness to delay the most dramatic claims until the tests are complete, even when the images tempt us to speak early. The discipline is psychological as much as technical, yet that discipline is also a kind of respect for the data. When you are working at the edge, you do not get to be casual about uncertainty. You have to carry it, quantify it, and test it from multiple angles. The reward is not just correctness, but credibility that survives scrutiny. But the cost buys something priceless. It buys a timeline of cosmic dawn that is anchored to proof, not to the seduction of extreme colours, and it buys confidence that survives reanalysis. In science, durability is a form of beauty. Now we confront the cosmology impact directly. If imposters are removed, the inferred number density of galaxies at Z greater than 10 can drop, and that drop propagates through every derived quantity. Counting errors at the top end can distort the entire story. A lower number density changes the bright end of the luminosity function. It can soften early claims that galaxies assembled too quickly, or that star formation was too efficient, because the brightest points exert disproportionate leverage. The bright end is where theory feels the most pressure. The leverage is mathematical as well as psychological. Luminosity functions are often fit with steep slopes, and the rare bright objects anchor the fit's high luminosity tail. If those anchors are imposters, the inferred tail can be artificially fat. A single correction can shift the inferred slope and normalization. It also shifts inferred star formation rate densities. If fewer galaxies are real at the highest redshifts, the integrated UV output declines, and the decline can change how we interpret the universe's early energy budget. In plain terms, it changes how much light we think existed. That matters for reionization. The timing and pace of reionization depend on how many UV photons early galaxies produced, and how easily those photons escaped, and both factors are inferred indirectly. A contaminated sample can make reionization look easier than it really was. When you remove imposters, you may find that galaxies still reionize the universe, but with tighter constraints on escape fractions and faint end contributions. The story becomes less about miraculous early giants, and more about the collective work of many smaller systems. That shift is not less interesting, it is more physical. Removing imposters can delay the apparent onset of vigorous star formation. It can also reduce the need for exotic physics that was invoked to explain impossible early brightness, because the impossibility may have been a bookkeeping error. Sometimes the universe is not breaking the rules. We are. Yet refinement is not erasure. The earliest galaxies still exist, and JWST has confirmed many with spectroscopy. But the extreme frontier must be remeasured carefully, with the same rigor we apply to nearer epochs. The frontier is real, but it is not immune to illusion. The story becomes more credible, not less dramatic. A corrected census can still show rapid growth, but it will show it within tighter uncertainties, and those uncertainties are where honest cosmology lives. Precision does not kill wonder. It concentrates it. This is the climax lesson of the series. JWST did not only reveal the first galaxies, it revealed the failure modes of our fastest discovery shortcuts. And it did so by making the faint universe accessible. When capability increases, so does the need for skepticism. The bullet cluster imposters become a warning label for every deep field. The deeper we go, the more the Milky Way can haunt the same colour space, and the haunting is not random. It is structured by astrophysics, by chemistry, and by the geometry of our own galaxy. And that haunting is not a nuisance. It is a scientific dividend, because the same searches also uncover the galaxy's coldest, faintest wanderers, objects that bridge the gap between stars and planets. The catalogue of contaminants becomes a catalogue of neighbours. By chasing the first light, we uncovered ancient darkness nearby. The overlap forces us to draw a sharper boundary between our galaxy and the universe, and to admit that the boundary is not obvious in a single image. It must be constructed with evidence. The boundary is not drawn by distance alone. It is drawn by tests that separate cosmological redshift from atmospheric chemistry, and stationary background from moving foreground, and statistical expectation from seductive outliers. The boundary is a method, so we return to the opening hook, now inverted. The edge of the universe moved closer because the dots slid sideways, and the sideways motion became a truth test, a simple, geometric signature that no early galaxy could counterfeit. The universe did not shrink, our interpretation sharpened. The central question sharpens into a method question. If those dots were not first galaxies, what else in our catalogues is wearing the same disguise, and how many times have we been fooled without noticing? The question is unsettling because it points inward. The answer is not paranoia, it is procedure. Photometry selects, spectroscopy confirms, multi-epoch imaging verifies. Modelling predicts what should contaminate, and the predictions are checked against reality. Procedure is how curiosity becomes knowledge. This is how JWST-era astronomy stays honest at the limit. It treats every extreme claim as provisional until it passes tests that imposters cannot pass, and it builds those tests into the observing plan rather than adding them as an afterthought. Honesty is engineered. The transition is unavoidable because the mystery has changed shape again. We're no longer asking only what the dots are, but what their disguise did to our timeline, and how that timeline should be rebuilt with stricter rules. The stakes are not just classification, they are history. In the final chapter, we resolve the identity with spectra and context, then rebuild the cosmic dawn story with stricter rules. We end with a better map and a better humility about what faint red light can mean, especially when the Milky Way is standing in the way. The central question has been hanging over every frame since the first detection, like a quiet hum beneath the data. If those two faint red dots were not galaxies from the first 200 million years, then what were they really? In the original images they looked almost ceremonial, two pinpricks of ember red light, suspended in a field of colder stars and distant smudges. The answer arrives without romance, and that is why it is decisive, because it does not need a story to support it. They were not primordial galaxies at all. They were ultra-cool, drifting substellar objects inside the Milky Way, faint enough to hide in plain sight until JWST made the infrared sky feel crowded. The case begins with the 1-year proper motion measurement because geometry does not negotiate, and distance has consequences. A true Z, greater than 10 galaxy, cannot slide across the sky on human timescales, not even by a fraction of a detector pixel. These sources did, and the shift was small enough to miss at a glance, yet large enough to overturn the entire interpretation. On screen, the movement looks almost like a magician's misdirection. Everything else stays pinned, while the red dots subtly drift. The shift is small in pixels and huge in meaning, because it collapses distance in a single unforgiving step. Proper motion at that level implies tens of parsecs to a few hundred parsecs, not billions of light years, and no lensing configuration can manufacture that motion. Proper motion is not an aesthetic detail, it is the sky's built-in ruler. Nearby objects appear to move because we observe them from a platform that is itself moving, and because their own velocities are not negligible. Distant galaxies, even when magnified, are effectively fixed to the celestial sphere. When a candidate moves, it stops being a cosmological question and becomes a local one. The year mattered because time became an instrument, not a delay, and the instrument was Earth's orbit. A single deep image can only suggest identity through colour, shape, and statistical expectation. Two images separated by months can test proximity through motion, because the baseline turns the telescope into a kind of astrometric lever. If the dot shifts against the background, it is telling you it lives in the same gravitational neighbourhood. Patience becomes methodology when the frontier is crowded with lookalikes, and JWST makes that crowd visible. The team waited because the claim was extraordinary and the degeneracies were known, even if they were easy to forget in the excitement. The extra year turned suspicion into a measurement, and the measurement turned a headline into a classification. There's also a psychological weight to waiting, because the universe does not reward impatience with clarity. In the first pass, the candidates were not absurd, they were plausible in exactly the way the most dangerous imposters are. They sat where early galaxies are expected to sit, in the colour space carved out by the dropout method. Their faintness made them feel ancient, and their redness made them feel distant. With motion established, the remaining question becomes what kind of local object can mimic cosmic dawn colours without being a galaxy. The photometry looked like a textbook dropout, with flux vanishing in bluer filters and persisting in redder ones. That pattern is real, but it is not unique, and the universe is under no obligation to keep our categories separate. At extreme redshift, the missing light is caused by neutral hydrogen and the intergalactic medium, which act like a fog bank for ultraviolet photons. The Lyman break cuts off res frame ultraviolet at 121.6 nanometers, and expansion shifts that cutoff into JWST's near-infrared bands. The dropout method is built on that universal physics, and it has powered decades of discoveries from Hubble to JWST. Historically, this approach was a triumph of simplicity, because it turned a complex spectrum into a practical search tool. In the 1990s, Lyman break selection helped identify star-forming galaxies at redshifts of 3 and 4, when spectroscopy for every faint source was impossible. The method matured into a pipeline: find the break, estimate a redshift, then follow up with deeper data. JWST simply pushes that same logic into a regime where the break moves into longer wavelengths, and the sky contains new kinds of imposters. In ultra-cool atmospheres, the missing light is caused by molecules and pressure, not by cosmological absorption. Methane and water carve deep absorption troughs, and H2 collision-induced absorption suppresses broad regions of the near-infrared. Those troughs can align with filter edges and imitate a single sharp break, especially when the data are faint and the filters are broad. This is the spectral coincidence that fooled the first pass, and it is a coincidence made more likely by sensitivity. Broadband filters compress complex spectra into a few numbers, and those numbers can be consistent with more than one physical story. A methane-shaped spectrum can land inside the same selection box as a Lyman break galaxy, and it can do so with unsettling confidence. If you could see the spectrum as a landscape, the difference would feel obvious. A high redshift galaxy is defined by one dominant cliff, where the flux drops because the universe itself blocks the bluer light. A cold substellar object is a terrain of ridges and valleys, repeating absorption features that rise and fall across the near-infrared. Photometry, however, is a set of wide buckets, and buckets are not designed to preserve fine structure. Spectroscopy resolves the coincidence by replacing buckets with structure, and structure is where physics leaves fingerprints. A cold substellar spectrum shows repeated molecular absorption complexes across the near-infrared, with methane bands and water bands appearing in predictable places. A high redshift galaxy shows one main break tied to redshift, plus a different continuum and possible nebular lines from ionized gas. Even when lines are weak, the overall shape tells you whether you're looking at an atmosphere or a population of stars. In this case, the spectral shape points to ultra-cool brown dwarfs, or closely related substellar bodies, rather than any plausible galaxy at cosmic dawn. The methane and water signatures explain the false high redshift colours with no additional assumptions. The point-like morphology and the measured motion fit the same story, and the story holds together under every test that matters. Brown dwarfs occupy a strange middle ground, too small to sustain hydrogen fusion like a star, yet often more massive than giant planets. Over billions of years they cool, fading from warm infrared sources into objects that glow weakly at temperatures not much higher than an oven. Their atmospheres become chemically rich, and their spectra become dominated by molecules that would be destroyed in hotter stars. In that cooling, they also become excellent mimics of distant galaxies, because both are faint and both can appear extremely red. The conclusion is direct and unglamorous, and it lands with the firmness of a solved puzzle. These were not the first galaxies turning on, they were ancient, faint wanderers nearby, glowing weakly in the infrared and drifting across our line of sight. The red dots did not belong to the dawn of starlight, they belong to the quiet afterlife of failed stars. Visually, the shift in meaning is dramatic, even if the images are not. What looked like the edge of the observable universe becomes a local census entry, a dot with a measurable trajectory. The background galaxies remain where they are, like wallpaper fixed to the sky, while the imposters betray their nearness by moving. It is a reminder that the sky is not a flat dome, it is a layered volume. Now the story pivots again, because the twist is not only about misclassification. It is about what JWST's sensitivity does to every search at the limit, and how it changes the balance of what is rare and what is merely faint. The deeper we go, the more the Milky Way can appear in the same colour space, because we are finally sensitive to its coldest, dimmest residents. What we learned about cosmic dawn searches is not that the dropout method failed, because it did what it was designed to do. It worked as triage because it found objects with the right missing light signature and flagged them for attention. The failure would have been treating triage as confirmation, as if a colour cut could substitute for a physical diagnosis. Dropout selection is powerful because hydrogen physics is strong, and the break is dramatic, and because the intergalactic medium is not subtle. Yet it is not infallible because other physics can create cliffs, and cold atmospheres are particularly good at it. JWST's depth makes those other physics visible in fields once considered clean, because the contaminants were always there. We simply did not see them. The headline problem is statistical as much as technical, and statistics becomes unforgiving when the expected numbers are tiny. At z greater than 12, the expected number of real galaxies in a given field is small, even in optimistic models. When samples are tiny, one imposter can distort luminosity functions and inflate narratives, and the distortion can ripple into theory. A single bright candidate at extreme redshift can tempt us into rewriting early star formation, because brightness implies mass and mass implies rapid assembly. If that candidate is actually local, then the pressure for exotic explanations evaporates, and the models breathe again. This is why the discipline of confirmation is not a bureaucratic burden. It is the difference between a real anomaly and a mirage. This is why confirmation standards must harden in the JWST era, especially for record-breaking claims that will anchor future work. Extreme candidates need orthogonal tests that imposters cannot pass, and the tests must be built into the workflow rather than added as an afterthought. Motion and spectra are the two simplest gates, and they are powerful precisely because they ask different questions. The one-year baseline becomes a new rule of thumb, not a special trick reserved for unusual cases. Multi-epoch imaging screens out nearby interlopers early and cheaply, because proper motion is a binary discriminator at these distances. It also catches transients that could masquerade as dropouts in single-epoch catalogues, including supernovae or variable stars that happen to be faint in the wrong filter. Time does not just reveal motion, it reveals change. Spectroscopy becomes the second gate, because it tests the cause of missing light rather than the appearance of missing light. It can locate a true Lyman break at a specific wavelength, and it can reveal line patterns consistent with a galaxy, even if the lines are faint. It can also expose the repeating troughs of methane and water, which no early galaxy spectrum should display. Better photometry still matters, but it must be designed to break degeneracies rather than merely deepen the same ambiguity. More filters can sample multiple molecular troughs and peaks, and that sampling can turn a false cliff into a recognizable pattern. A Lyman break is a single cliff, while a cold atmosphere is a repeating landscape, and landscapes reveal themselves when you take enough measurements. Templates and priors also have to grow up, because algorithms are only as skeptical as we allow them to be. Photometric redshift codes choose among the options they're given, and they assign probabilities based on training sets and assumptions. If ultra-cool dwarfs with varied gravity and metallicity are missing, the code will prefer extreme redshift by default. In that sense, a false galaxy can be an artifact of an incomplete library. The bullet cluster field adds a specific caution, because lensing amplifies both signal and temptation, and it does so in a visually compelling way. Magnification can elevate a faint foreground object into detectability, and it can make it appear more significant than it is. It can also bias attention toward dramatic regions where we expect high redshift, because the human mind likes a narrative that matches the scenery. Lensing models matter for inferred intrinsic brightness, and they matter for turning observed flux into a claim about mass and star formation. Yet they cannot explain away motion, because lensing does not create a drifting centroid against fixed background galaxies. The proper motion result cuts through lensing uncertainty like a straight edge. It tells us the object is local, regardless of magnification, regardless of where it sits in the cluster's gravitational map, so the mystery reframes itself from discovery to discipline, and that reframing is the real maturation of the field. The edge of the universe remains a real target, but it is now guarded by procedures that acknowledge how crowded the parameter space has become. The procedures are not bureaucratic, they are how we keep wonder honest. They are how we keep the frontier from becoming a hall of mirrors. This reframing is also a win for cosmology, not a retreat from it, because it strengthens the chain of inference. Removing imposters makes the early galaxy census more accurate, and accuracy is what theory needs. It reduces pressure for exotic explanations that were driven by contaminated samples, and it prevents us from building castles on misidentified dots. A cleaner sample tightens constraints on star formation efficiency and early halo growth, because the bright end of the luminosity function is where models diverge most. It refines the bright end of the luminosity function, which is sensitive to rare objects and therefore sensitive to contamination. It clarifies how rionization could proceed without invoking miracles, because the timing depends on how many real galaxies exist and how efficiently they produce ionizing photons. The discovery also becomes a win for local galactic archaeology, because the imposters are not noise and not a disappointment. They are data points from a hidden population, and hidden populations are how galaxies reveal their history. JWST is revealing an inventory of old, cold, faint objects that earlier surveys missed, not because they were absent, but because they were effectively invisible in the wavelengths we used. These bodies are hard to find because they are intrinsically dim and optically invisible, and because their spectra are shaped to hide them from traditional searches. Their temperatures push emission into the infrared, and their atmospheres absorb much of what remains, leaving only narrow windows where photons escape. Traditional catalogues were built in the wrong bands and at insufficient depth, so the census was always incomplete. JWST changes that by making deep infrared imaging routine. Deep extragalactic programs accidentally become the best traps for local cold wanderers, and the irony is productive. They stare long enough to detect what all sky surveys average away, because integration time turns faint into measurable. They also avoid bright stars, which makes faint substellar sources stand out when they appear, like a single coal glowing on a dark floor. In these quiet fields, even a nearby wanderer cannot hide behind glare. The Milky Way implication is simple and unsettling, because it suggests our neighbourhood is more populated than our maps admit. There may be many more old brown dwarfs and rogue planetary mass objects drifting through the disk and thick disk than we have counted. Some may belong to the halo and carry signatures of early galactic chemistry, preserved in their atmospheres like a fossil record. If so, they are not just curiosities, they are probes. Their kinematics can hint at ancestry, because motion is a form of membership, and membership is a form of history. Disk objects tend to share rotation with modest dispersions, moving in broadly similar directions around the galactic centre. Thick disk and halo objects move faster and more eccentrically, reflecting older, merger-built populations whose orbits were stirred long ago. When a faint dot moves unusually, it may be telling you it comes from an older component. Parallax would sharpen distance and separate true velocity from proximity, and it would do so with the same geometry that made proper motion decisive. With enough epochs, the annual wobble becomes measurable even for faint sources, because Earth's orbit provides a known baseline. That turns a drifting dot into a mapped neighbour with a place in the galaxy, and it turns speculation into a three-dimensional coordinate. Distance is the key that unlocks luminosity, and luminosity is the key that unlocks physical interpretation. The classification boundary between brown dwarf and rogue planet remains physically meaningful and observationally difficult, and the difficulty is not just semantics. Without a dynamical mass, origin is ambiguous because formation history is not written plainly on the spectrum. At a few hundred Kelvin, different formation histories converge to similar spectra, and the atmosphere does not volunteer its past. The same molecular bands can belong to an object born in a disk or an object born like a star. Yet the ambiguity does not weaken the conclusion, because the conclusion is about category, not pedigree, and the category is clear. These are substellar objects in the Milky Way, not galaxies at cosmic dawn, and that distinction is what the measurements demand. Their disguise teaches us where our methods are brittle, and brittleness is valuable knowledge when the stakes are high. It tells us exactly where to reinforce the workflow. The deeper theme is that the boundary between near and far is not a line, and it never has been, even if our language suggests otherwise. It is a gradient shaped by physics, instrumentation, and interpretation, and gradients are where confusion thrives. The same infrared glow can belong to the first starlight or to a cold neighbour, and the detector does not care which story we prefer. It simply counts photons. JWST sits exactly on that overlap, by design and by consequence, and that is part of its power. It was built to see ultraviolet stretched into infrared from the early universe, which means it is tuned to the red-shifted signatures of cosmic dawn. It therefore also sees the infrared native emission of ultra-cool bodies nearby, because those objects live in the same wavelength regime. The telescope is not confused, but our categories can be. That overlap is not an accident that will go away with better luck or a single improved catalogue. It is a permanent feature of the parameter space we are now exploring, and permanence changes strategy. As sensitivity increases, the overlap region becomes more populated and more important, because we are sampling deeper into both extremes at once. The frontier is not just farther away, it is also closer than we thought, so the practical lesson becomes part of the story's ending, and it is as much about process as it is about discovery. Photometry selects and excites, but it cannot be the final word because it is built to be fast and inclusive. Motion and spectra must be built into the workflow for any record-breaking claim, because they answer questions that colour alone cannot answer. The goal is not to slow down the search, but to keep it anchored. This is not a call for caution that kills discovery, and it is not a retreat into timidity. It is a call for tests that make discovery durable, so that the next extraordinary claim survives contact with skepticism. The universe did not trick us to embarrass us, it tricked us to refine us, because refinement is how science turns surprise into knowledge. The bullet cluster red dots are now understood as imposters, but they are also teachers, and teachers are often unglamorous. They show that our search for the first galaxies runs through the Milky Way's faintest outskirts, where cold objects drift quietly. They show that deep time and local space can share the same colours, and that colour is not identity. They also show how easily a compelling context can bias interpretation. In that sense, the edge of the universe did not move closer in reality, and the early galaxies did not vanish from the cosmos. Our map moved closer to the truth, and the truth is often more layered than the first story. The same telescope that reaches toward the Big Bang also exposes a hidden census of ancient wanderers nearby, and it does so in the same frames. One dataset can contain two kinds of frontier. We end where we began, with two pinpricks that changed meaning when we watched them long enough, and watching is the theme. A year later, they slid sideways across the sky, almost casually, as if they had always been moving and we had simply failed to notice. The motion was the confession, and the confession sharpened the frontier. It turned an apparent cosmological monument into a local traveller. The cosmos still has an edge we are trying to see, and JWST will keep pushing toward it with deeper fields and better instruments. Yet that edge is now patrolled by imposters that force better questions, and better questions are the real currency of progress. In the faint infrared, the end of the galaxy and the beginning of the universe blur, and only careful tests tell us which darkness we are truly seeing. We began with two ember-red pinpricks in JWST's bullet cluster field, flagged as near-perfect dropouts, and for a moment they looked like first light. We tested every easy failure mode, weighed lensing's power against its traps, and watched how photometric redshifts can harden into headlines when the data are faint. Then we let time do what templates cannot, and the sky answered with a sideways drift. turning a cosmic dawn claim into a local mystery. That single geometric fact forced every chapter's lesson into focus, because the same infrared darkness can belong to opposite ends of the distance ladder. A Lyman break from neutral hydrogen at the dawn of reionization can paint the same broadband cliff as methane and water in a freezing atmosphere nearby. In lensing fields where magnification, critical curves, and model disagreements can reshape what we think we see, the risk is not just contamination, it's confidence. So the story became less about being fooled, and more about building a workflow that deserves the faintest photons, motion checks, wider filter baselines, stronger priors, better contaminant libraries, and spectroscopy as a second gate. And in that reversal, JWST didn't lose its purpose, it widened it. Because the telescope built to find the first galaxies also exposes the coldest wanderers, the Milky Way's hidden embers drifting through deep fields. Those moving dots may still resolve into late T or Y dwarfs, metal-poor halo strays, or even free-floating planetary mass worlds, but the method for deciding is now clear. Spectra will tell whether the missing light is carved into one sharp cosmic edge, or into many molecular troughs, and parallax will pin their distances like a thumbtack on the galaxy's map. Meanwhile, the bullet cluster remains both a magnifying glass and a funhouse mirror, reminding us that lens models must be treated as measurements, not assumptions, when a single object can bend an entire early universe narrative. This is the earned closure of the journey. The universe didn't trick us to embarrass us, it tricked us to refine us, and the refinement is the point. When JWST pushes into the distribution tails, where true Z greater than 12 galaxies are rare and contaminants are suddenly common, discipline becomes discovery's closest companion. If we want the bright end of the cosmic dawn luminosity function to mean anything, we must be willing to subtract our most exciting candidates until only the unmovable ones remain. That is how cosmology stays honest, not by avoiding mirages, but by learning to recognize them quickly and to ask for the kind of evidence that cannot be mimicked. Even now, there is a productive tension left on the table, because we have not yet watched the final verdict arrive in spectra, line patterns, and precise distances. The next observations will not just label two objects in one field, they will set a standard for every future claim made at the edge of time. In the JWST era, red is no longer an answer, it is only an invitation to test. And perhaps that is the deeper revelation, that the edge of cosmic time and the outskirts of our own galaxy overlap in the same faint infrared glow, and only careful, orthogonal truth tests can tell which darkness we're truly seeing. So if those two faint red dots weren't galaxies from the first 200 million years after the Big Bang, what were they really? They were nearby cold wanderers wearing the universe's oldest disguise, and their sideways motion revealed the rule we can't break. The dawn of time must be confirmed by geometry and spectra, not colour alone. In the end, JWST didn't just show us farther, it showed us how to look, with patience sharp enough to separate ancient light from local night. The first galaxies are still out there, but the path to them runs straight through our own backyard, where even the smallest drifting ember can teach us what distance truly means. If you want to follow what happens next, watch for the spectra and the parallax, because the next great cosmic dawn discovery will be the one that survives every test.